Hello there, and welcome to Science for Sleep, where curiosity gets cozy and the universe slows its pace just enough for you to settle into a comfortable corner of the night. Wherever you happen to be listening from, whether it is a quiet bedroom with the lights dimmed low, a long drive with the road humming beneath you, or a pair of headphones wrapped gently around your thoughts, I'm glad you've arrived here for a little while. Tonight, we're going to wander through something vast and familiar at the same time, something you have almost certainly seen but maybe never truly met. We're going to talk about the real shape of the Milky Way, the enormous star-filled home that holds our tiny planet like a speck of dust caught in a beam of light. Before we drift too far into that glowing expanse, let me ask you something simple and grounding. Where are you right now, and what does the world around you sound like? Maybe there is the soft whir of a fan, the distant rush of traffic, or the gentle breathing of someone nearby. And what time is it in your corner of Earth as you listen to this? There is something quietly fitting about thinking of time and place while talking about a galaxy so large that light itself takes 100,000 years just to cross from one side to the other. If this calm little journey feels soothing or even just mildly interesting, a small gesture like a like or a subscription helps this space reach other curious, tired minds looking for something gentle to end their day with. But for now, there is nothing you need to do except listen and let your thoughts move at their own unhurried pace. Let us begin somewhere familiar. Think back to the last time you looked up at the night sky. Really looked. Not just a quick glance between buildings or through a windshield, but a moment where the stars had space to show themselves. If you have ever been far from city lights, you might remember a pale, cloudy band stretching across the darkness. It does not look like a sharp line or a neat pattern. It looks more like a soft spill of light, as if someone brushed a glowing fingerprint across the sky. For thousands of years, people have stared at that faint ribbon and wondered what it was. Some imagined it as a river of milk spilled by a careless god or a startled animal in the heavens. Others saw it as a path, a bridge, or a trail left behind by something divine passing overhead. Today, we know that what you are seeing is not a cloud or a river at all. It is the combined light of hundreds of billions of stars, packed so closely together in one direction that your eyes cannot separate them into individual points. You're looking across the flat plane of a vast stellar system, the one that holds our sun, our planets, and every human story that has ever unfolded. That system is the Milky Way galaxy. But here is the curious part. Even though we live inside it, even though we are made from the same cosmic material as its stars and dust, we cannot simply step back and see its full shape. Trying to map the Milky Way from within is a bit like trying to understand the shape of a forest, while standing in the middle of it, surrounded by trunks, branches, and leaves in every direction. So what does our galaxy actually look like? Is it a neat, flat disk like a glowing pancake floating in space? Is it a graceful spiral with arms curling outward like the petals of a cosmic flower? Or is it something messier, warped and bent by forces we are only beginning to understand? The answer, as it turns out, is a little bit of all of those things, and the path to discovering it has been a long, careful process of observation, patience, and more than a few clever tricks. To appreciate how far we have come, it helps to start with what people once believed. For much of human history, the Milky Way was not thought of as a structure at all, but as part of the sky itself, a decorative feature painted onto a vast, mysterious dome. Ancient Greek philosophers debated whether it was a phenomenon of the atmosphere or something truly celestial. In China, it was known as the Silver River, separating two star-crossed lovers in a famous story. In many cultures, it was woven into myths that tried to explain not its shape but its meaning. The shift from story to structure began when people started building better tools to look at the sky. In the early 17th century, Galileo Galilei pointed one of the first telescopes toward that cloudy band and saw something remarkable. Instead of a smooth glow, he found countless faint stars, packed so tightly together that they blended into a soft haze when seen with the naked eye. This was a quiet but profound revelation. The Milky Way was not a mist or a smear of light. It was a vast collection of individual suns stretching far beyond what anyone had imagined. Even with that knowledge, the true shape of the galaxy remained elusive. In the 18th century, an English astronomer named William Herschel tried a method that now feels both simple and ambitious. He counted stars in different directions, assuming that more stars meant more distance and fewer stars meant an edge. By doing this again and again, he built a rough map of what he thought the Milky Way looked like. His version placed the Sun near the centre of a flattened oval-shaped system, like a thick disk of stars floating in space. It was a reasonable guess based on the information he had, but it was also wrong in an important way. Herschel did not know about interstellar dust, tiny grains of material scattered between stars that absorb and block light. In some directions, this dust hides huge portions of the galaxy from view, making it seem as though there are fewer stars and that the galaxy ends there, when in reality it continues far beyond what his telescope could see. It is a bit like trying to map a city while heavy fog fills some of the streets. You might think the city is smaller than it really is simply because you cannot see through the haze. As telescopes improved and photography entered the scene, astronomers began to notice dark patches cutting through the bright band of the Milky Way. These were not empty spaces, but dense clouds of dust and gas, the raw material for future stars. They gave the galaxy a mottled, uneven appearance, full of bright clusters and shadowy lanes. The more closely people looked, the more complex it seemed. The early 20th century brought another leap forward, driven by a debate that sounds dramatic enough to belong in a novel. At the time, many astronomers believed that the Milky Way was the entire universe, and that the faint, fuzzy objects called spiral nebulae were small clouds of gas and stars within it. Others suspected that these spirals were something much larger, entire galaxies in their own right, far beyond the boundaries of our own. The question was settled by Edwin Hubble, who measured the distance to one of these spirals and found that it lay far outside the Milky Way. The universe suddenly became much bigger. That discovery also changed how people thought about our own galaxy. If those distant systems were spirals, perhaps the Milky Way was one too. But again, being inside it made confirmation difficult. Imagine trying to determine whether a city is laid out in a spiral pattern while walking through its streets at night, with tall buildings blocking your view in every direction. You might notice curves here and there, but the overall design would be hard to grasp. So astronomers turned to indirect methods. One of the most important tools in this effort has been radio astronomy. While visible light is easily blocked by dust, radio waves can pass through it more freely. In the mid-20th century, scientists began mapping the Milky Way using the radio signal emitted by hydrogen atoms, the most abundant element in the galaxy. By measuring the motion of this hydrogen, they could trace out large-scale structures that were otherwise hidden from view. These maps revealed that the Milky Way is indeed a spiral galaxy, with long, sweeping arms of stars, gas and dust curving outward from a dense central region. Our Sun is not near the middle, but rather tucked away in one of these arms, about halfway between the centre and the outer edge. This alone is a humbling thought. When you look up at the night sky, you're not gazing out from a place of cosmic importance. You're looking out from a quiet suburb of a vast stellar city. But even this description is only part of the story. The Milky Way is not a perfectly flat, orderly spiral. Its central region is not just a simple cluster of stars, but a bar-shaped structure, a long, dense band of stars stretching across the core. From the ends of this bar, the spiral arms appear to emerge, giving the galaxy what astronomers call a barred spiral shape. If you could float far above the galaxy and look down on it, you would see something like a glowing pinwheel with a bright straight line across its centre. The disk of the galaxy itself is thin compared to its width, but it is not rigid. It is warped and twisted, especially near the outer edges. Instead of lying flat like a vinyl record, it bends slightly up and down, forming a gentle wave. This warp may be caused by the gravitational pull of nearby galaxies, like the Large and Small Magellanic Clouds, or by the distribution of dark matter surrounding the Milky Way. Even on the scale of hundreds of thousands of light-years, the galaxy is not isolated. It is part of a slow, subtle dance with its neighbours. Then there is the halo, a vast faint region that surrounds the bright disk. The halo contains old stars, star clusters, and most importantly, a massive amount of dark matter. This dark matter does not emit or absorb light, but its gravity shapes the motion of stars and gas in the galaxy. Without it, the Milky Way would not hold together the way it does. The stars in the outer regions would drift away, no longer bound by the gravity of the visible material alone. The halo gives the galaxy a kind of invisible, extended shape, far larger than what we can see directly. All of this raises a quiet, almost philosophical point. When we ask about the real shape of the Milky Way, we're not just asking about the arrangement of stars. We're asking about something that is partly visible and partly hidden, something defined as much by what we cannot see as by what we can. The glowing spiral arms, the bright central bar, the thin warped disk, and the vast shadowy halo all combine into a structure that is both elegant and complex. As you listen to this, consider the scale of what we're talking about. Light, the fastest thing in the universe, takes about 8 minutes to travel from the Sun to Earth. To cross the Milky Way from one side to the other, it takes roughly 100,000 years. Every point of a light you see in that soft band across the sky is separated from its neighbours by distances so large that even our best spacecraft would take millions of years to reach them. And yet, they are all part of the same structure, all moving together through space as a single, enormous system. What makes this even more remarkable is that our understanding of the galaxy's shape is still evolving. New missions, like the Gaia spacecraft, are measuring the positions and motions of billions of stars with unprecedented precision. These data are revealing subtle ripples and patterns in the disk, hints of past encounters with smaller galaxies that have left their marks like faint scars. The Milky Way, it seems, is not a static object. It is a living structure, shaped by collisions, mergers, and the slow flow of stars and gas over billions of years. Somewhere deep in its centre, hidden behind thick curtains of dust, lies a supermassive black hole, about 4 million times the mass of the Sun. Around it, stars orbit at incredible speeds, tracing out tight loops in the intense gravitational field. This central region anchors the entire galaxy, yet it is also one of the hardest parts to observe directly. Again, the shape of the Milky Way is defined by both presence and absence, by what we can measure and what we have to infer. Step outside for a moment, at least in your imagination, and let the ground beneath you feel steady and familiar. Picture the air as it is right now, maybe cool, maybe warm, carrying the faint scent of night, or the leftover warmth of a day that has not quite let go yet. Above you, stretching in every direction, is the sky, an open space that has watched over countless lives, long before cities, long before names, long before anyone thought to measure the hours. This is where our view of the Milky Way begins, not with instruments or equations, but with a simple human habit, tilting the head back and wondering what all that darkness is made of. For most people, the first encounter with the Milky Way is not dramatic. It does not burst into view like a fireworks display or announce itself with a sharp edge. Instead, it appears quietly, almost shyly, as a soft, uneven band of light stretching from one horizon to the other. In places far from artificial lights, it can look like a pale cloud brushed across the night, thicker in some areas, thinner in others, with dark lanes cutting through it like rivers of shadow. It is easy to mistake it for a patch of thin cloud or a trick of tired eyes, And yet this gentle glow is the combined light of more stars than anyone could count in a lifetime, all layered on top of each other from our point of view on a small planet in one corner of a very large system. When you look at the Milky Way from Earth, you're not seeing it from the outside, like a picture in a book or a glowing spiral in a science documentary. You're seeing it from the inside, from a seat embedded in its disk. That simple fact shapes everything about how it appears in the sky. Imagine standing in the middle of a long, straight road lined with streetlights that stretch off into the distance in both directions. If you look along the road, the lights will seem to crowd together, forming a bright line that fades into a blur far away. If you turn and look to the side, you might only see a few lights scattered here and there. The Milky Way works in a similar way. When you look along the flat plane of the galaxy, you see the dense concentration of stars that form that glowing band. When you look away from it, up or down out of the galactic plane, the sky becomes darker and more sparsely dotted. This perspective explains why the Milky Way arches across the sky in a great curve. As Earth rotates, that band slowly shifts position, rising and setting like a very slow, very quiet tide of light. In the summer months in the Northern Hemisphere, the brightest and most detailed part of the Milky Way is often visible in the evening sky, especially in the direction of the constellation Sagittarius, which points roughly toward the centre of the galaxy. In the winter, a different, fainter stretch of the band takes its place, showing more of the galaxy's outer regions. From the southern hemisphere, the view is even richer, with the galactic centre climbing higher in the sky and revealing a denser, more intricate pattern of stars and dark clouds. Those dark clouds are one of the most striking features when you begin to really pay attention. They are not gaps where nothing exists. They are thick regions of interstellar dust and gas, cold and dense enough to block the light of the stars behind them. Against the glowing background of the Milky Way, they appear as inky silhouettes, twisting and branching like smoke frozen in place. For centuries, these dark shapes puzzled observers. Some thought they were simply empty holes in the starfield. It took the development of astrophotography and infrared astronomy to reveal that these shadows are actually some of the most active and important regions in the galaxy. Inside them, new stars are being born, slowly collapsing out of clouds of gas and dust, hidden from view until their light is strong enough to break through. Long before anyone knew that, people found meaning in what they saw. Different cultures across the world gave names and stories to the Milky Way, each shaped by the landscape, beliefs, and daily rhythms of the people who looked up at it. In ancient Greece, it was linked to the story of Hera and the infant Hercules, with the band of light said to be milk spilled across the sky. In China, it became a celestial river separating two lovers, represented by the stars Vega and Altair, who are allowed to meet only once a year. For many indigenous cultures in the Americas and Australia, the Milky Way was a path of spirits, a road for ancestors, or a map that mirrored important features of the land below. What all of these stories have in common is a sense that this faint, glowing structure was more than just a decoration in the sky. It was a presence, something that connected the human world to a larger unseen order. Even today, with all our scientific explanations, that feeling can still surface when you find yourself under a truly dark sky. There is a subtle shift that happens when you realise that the soft band overhead is not a distant object, but a sideways view of the place you live in on a cosmic scale. From a more practical standpoint, the Milky Way has also been a guide. Before compasses and GPS, travellers used the stars to find their way, and the broad arc of the galaxy could help orient them at night. In some parts of the world, it was used to mark the changing seasons, its position in the sky shifting over the course of the year as Earth moved along its orbit around the Sun. The sky, in this sense, became a kind of slow, reliable calendar, with the Milky Way as one of its most prominent features. The way the Milky Way appears to your eyes is shaped not only by your position in the galaxy, but also by the limitations of human vision. Our eyes are more sensitive to brightness than to fine detail in low light. When you look at a star, you're usually seeing it as a sharp point. When you look at a region packed with millions of faint stars, their light blends together into a smooth glow. This is why the Milky Way looks like a cloud rather than a dense field of individual points. If you use binoculars or a small telescope and sweep along the band, the transformation can be surprising. The hazy glow resolves into countless tiny stars, layered at different distances, some bright and nearby, others faint and far away. Photographs taken with long exposures push this effect even further. They reveal colours and structures that are invisible to the naked eye. Soft reds from glowing hydrogen gas, blues from hot young stars, and intricate networks of dark dust lanes appear in these images, turning the Milky Way into a richly textured tapestry. It is worth remembering, though, that these images are not exactly what your eyes would see, even if they were more sensitive. They are a translation of light into a form we can appreciate, a kind of visual storytelling that highlights features of interest and compresses hours of collected light into a single frame. Another subtle factor that shapes our view is the atmosphere itself. The air above you is not perfectly still or perfectly clear. It bends and scatters light, especially near the horizon, where you're looking through a thicker layer of it. This is why the Milky Way often appears brighter and more detailed when it is high in the sky, and fainter when it is closer to the ground. Light pollution adds another layer of complexity. In cities and towns, artificial lights brighten the sky, washing out the faint glow of the galaxy. For many people, the Milky Way is something they have only seen in pictures, not because it is rare, but because it is delicate. It needs darkness to show itself. There is a quiet irony in that. The Milky Way contains the combined light of hundreds of billions of stars, yet it can be hidden by a single street lamp. This contrast says something about scale, about how vast and powerful things can still be easily overshadowed by something small and close at hand. It also explains why efforts to preserve dark skies have become more important to astronomers and nature lovers alike. Losing the Milky Way from view is not just a scientific issue, it is a cultural one, a loss of a shared experience that has connected people across time and place. When you do manage to find a truly dark spot, away from the glow of cities, the experience can feel almost unreal. The band of the Milky Way becomes more structured, more alive. You can trace its path across the sky, notice where it thickens into bright knots of stars and where it thins into faint wisps. In some regions, especially toward the centre of the galaxy, the density of stars is so high that it can be hard to find patches of pure black sky between them. It is in moments like this that the idea of the galaxy as a flat disk begins to make sense. You're looking along its plane, through layer after layer of stars, each one a sun in its own right, each one potentially hosting its own set of worlds. One of the most intriguing aspects of the Milky Way as seen from Earth is how uneven it appears. The brightness is not uniform. Some sections glow strongly, while others fade into near invisibility. This unevenness reflects the true structure of the galaxy. The brighter regions often correspond to spiral arms, where stars are more densely packed, and where new stars are forming. The fainter stretches point toward areas with fewer stars or more dust blocking the light. By carefully mapping these variations, astronomers have been able to infer the large-scale shape of the Milky Way, even without a clear external view. This process of inference is a bit like trying to understand the shape of a building by walking through its hallways. You notice where rooms cluster together, where corridors stretch out, where walls block your path. Over time, a mental map begins to form. It may not be perfect, but it captures the general layout. In the same way, the view of the Milky Way from Earth, combined with measurements of star positions, motions and distances, has gradually revealed the galaxy's spiral nature, its central bar and its extended halo. Another layer of perspective comes from thinking about motion. The Milky Way you see tonight is not frozen in place. Earth is rotating, which makes the sky appear to turn over the course of a night. At the same time, Earth is orbiting the Sun, which changes which part of the galaxy is most prominent at different times of the year. On a much larger scale, the Sun itself is orbiting the centre of the Milky Way, taking about 230 million years to complete one full circuit. Every time the Sun completes one of these long, slow orbits, the continents on Earth have shifted, species have risen and fallen, and the sky has looked subtly different. This means that the view of the Milky Way has a history. The band that ancient people saw was not exactly the same as the one we see today, though the differences are far too small to notice in a single lifetime. Over millions of years, the positions of stars change, spiral arms drift, and new stars light up while old ones fade. The galaxy is not a static backdrop. It is a dynamic system, constantly in motion, even if that motion is measured in timescales far beyond everyday experience. There is also something quietly grounding about realizing that every culture, every generation, has looked up at this same structure. The details of the stories have changed. The tools for studying it have become more sophisticated, but the basic experience remains. A human being stands on the surface of a small planet, looks up at a glowing band of light, and feels a mixture of curiosity, wonder, and perhaps a slight sense of being very small in a very large place. From a scientific point of view, that feeling of smallness is matched by an appreciation for how much information is packed into what you see. The colour of the light, the way it fades and brightens, the presence of dark lanes, all of these are clues. They tell astronomers about the types of stars in different regions, the amount of dust and gas, and the processes shaping the galaxy. By combining this visual information with data from telescopes that can see in radio, infrared, and other wavelengths, a more complete picture emerges, one that goes far beyond what the eye alone can detect. Yet, for all that, there is value in the simple act of looking. You do not need to know about hydrogen emission lines or stellar populations to appreciate the Milky Way as a feature of the night sky. Sometimes, it is enough to notice how it stretches from one end of the horizon to the other, how it seems to cradle the darkness rather than interrupt it, how it can make the sky feel less like an empty void and more like a place filled with distant, quiet company. Long before anyone thought about galaxies as vast systems of stars held together by gravity, the Milky Way existed in the human mind as something closer to a story than a structure. When people looked up at that pale, wandering band in the sky, they did not see a disk or a spiral. They saw a presence. They saw a mark left behind by something powerful, or a pathway that connected the ordinary world below to a larger, unseen realm above. And in a way, those early interpretations were not entirely wrong. They were simply answering a different question. Instead of asking what the Milky Way was made of, they were asking what it meant. In ancient Greece, the faint ribbon of light was tied to a tale involving gods, infants, and a moment of celestial clumsiness. According to one version of the story, the baby Heracles was brought to the sleeping goddess Hera, so he could drink her milk and gain divine strength. When she woke and pushed him away, some of that milk spilled across the sky, leaving behind the glowing band that people would later call the Milky Way. The name itself comes from this idea, from the Greek galaxias, meaning milky. Even now, thousands of years later, we still carry that image in our language, a reminder that our scientific terms often have roots in very human attempts to explain what we see. In China, the same band of light became the Silver River, a celestial divide separating two lovers, the weaver girl and the cowherd, represented by the stars Vega and Altair. Once a year, according to the story, a bridge of birds would form across the river so they could meet. This narrative did not focus on the Milky Way as an object in itself, but as a boundary, a line that shaped relationships between the points of light scattered across the sky. The shape of the galaxy in this view was not something to be measured. It was something that defined space and connection. Across the world, in the lands of the Maya and the Aztec, the Milky Way was woven into a much larger cosmological framework. It was associated with the world tree, a central axis connecting the underworld, the earth and the heavens. The band of stars overhead mirrored this idea, stretching across the sky as a kind of cosmic backbone. In some interpretations, it was linked to the path of the sun through the sky and the cycle of life and death. Again, the focus was not on physical shape, but on position and role, on how this feature of the night sky fit into a broader understanding of how the universe was organised. For many indigenous cultures in Australia, the Milky Way was seen as a river or a road in the sky, a place where ancestors travelled and where stories were written in the stars. Dark patches within the glowing band were not empty spaces, but figures and creatures, shapes formed not by light, but by shadow. This is an important detail, because it shows a different way of reading the sky. Instead of focusing only on the bright points, these traditions paid attention to the dark spaces between them, turning absence into presence and emptiness into form. All of these perspectives shared a common feature. They treated the Milky Way as something flat, something stretched across the sky like a stripe on a vast dome. There was no sense that it wrapped around the Earth, or that it had depth extending far beyond what the eye could see. The sky itself was often imagined as a solid surface, a sphere or canopy with stars fixed into it like lanterns or jewels. Within that framework, the idea of a three-dimensional structure made of countless suns arranged in a disk or spiral would have been almost impossible to conceive. The shift toward a more physical understanding of the Milky Way began slowly, and it did not start with the galaxy itself, but with changing ideas about Earth. When ancient Greek thinkers like Aristotle argued that Earth was a sphere rather than a flat plane, they were also, indirectly, changing how people thought about the sky. If the ground beneath your feet was curved, then perhaps the heavens above were not just a simple roof, but part of a larger, more complex system. Still, for centuries, the dominant model of the universe in Europe placed Earth at the centre, surrounded by nested spheres carrying the moon, the sun, the planets, and the fixed stars. In this geocentric view, the Milky Way was often considered a feature of the outermost sphere, part of the realm of the stars, but not something with a distinct shape or structure of its own. It was more like a stain or a seam in the fabric of the heavens than a system in its own right. The first major crack in this way of thinking came with the telescope. When Galileo turned his instrument toward the Milky Way in 1610, he did not set out to map its shape. He was simply curious about what that hazy band was made of. What he found was both simple and revolutionary. The Milky Way, he wrote, was composed of a vast number of stars, so numerous and so close together that they blurred into a continuous glow when seen without magnification. This observation transformed the Milky Way from a mysterious cloud into a crowded field of individual objects. Once the idea of the galaxy as a collection of stars took hold, the next question was almost inevitable. How were those stars arranged in space? Were they spread out evenly in all directions, or were they clustered into some kind of form? Answering that question required more than just better telescopes. It required a way of thinking about distance on a scale far beyond everyday experience. In the 18th century, an astronomer named William Herschel took on this challenge with a method that was both ambitious and, in hindsight, beautifully straightforward. He assumed that stars were more or less evenly distributed throughout the Milky Way, and that his telescope could see all of them out to the edge of the system. With those assumptions in place, he began counting stars in different directions. Where he saw many stars, he reasoned that the galaxy must extend far in that direction. Where he saw fewer, he concluded that he was closer to the edge. By repeating this process again and again, Herschel built a rough three-dimensional map of what he thought the Milky Way looked like. His version was a flattened, lens-shaped system, thicker in the middle and thinner toward the edges, with the sun located near the centre. This was one of the first attempts to describe the galaxy's shape in physical terms rather than symbolic ones. It was a map, not a myth. The problem, as later astronomers would discover, lay in those initial assumptions. Stars are not evenly distributed, and telescopes cannot see through everything. Between many of the stars in the Milky Way lie vast clouds of dust and gas that absorb and scatter light. These clouds can make regions of the galaxy appear emptier than they really are. Herschel's star counts were, in effect, shaped by invisible walls. He was mapping not just the galaxy, but also the fog that lay within it. Even so, his work marked an important turning point. The Milky Way was now being treated as a system with a size, a shape, and a structure that could, at least in principle, be measured. The language of stories and symbols began to share space with the language of observation and calculation. The 19th century brought more powerful telescopes and the first attempts to photograph the sky. These images revealed details that the eye alone could not hold on to. Faint stars and subtle variations in brightness that hinted at a complex layered structure. Astronomers began to notice that the Milky Way was not uniform. It had brighter regions, darker lanes, and clusters of stars that seemed to trace out curved patterns. At the same time, a new class of objects, the so-called spiral nebulae, entered the conversation. These faint, fuzzy shapes, some of which showed clear spiral patterns in photographs, raised an intriguing possibility. If those distant objects were spirals, perhaps the Milky Way was one too, but opinions were divided. Some astronomers believed these nebulae were small, nearby clouds within our own galaxy. Others suspected they were entire star systems far beyond it. This debate came to a head in the early 20th century, in an event now known as the Great Debate. Two prominent astronomers, Harlow Shapley and Heber Curtis, argued publicly about the nature of the universe. Shapley believed the Milky Way was enormous and that the Sun was far from its centre, and he thought the spiral nebulae were part of it. Curtis argued that the Milky Way was smaller and that the spirals were separate galaxies in their own right. What is interesting, from the perspective of shape, is that both men were partly right and partly wrong. Shapley correctly placed the Sun away from the centre of the Milky Way, but he underestimated the role of dust in obscuring parts of the galaxy. Curtis was right about the spiral nebulae being other galaxies, but he underestimated the true size of our own. The resolution of this debate came with the work of Edwin Hubble, who measured the distances to some of the spiral nebulae and found them to be far outside the Milky Way. This discovery expanded the known universe dramatically, and it also gave astronomers a new way to think about our own galaxy. If other galaxies were spirals, perhaps the Milky Way was a spiral as well, seen from the inside. The challenge, of course, was how to confirm that without being able to step outside and take a picture. This is where the transition from visual observation to more abstract mapping really took hold. Astronomers began using the motion of stars and gas to trace out large-scale patterns. By measuring how fast different parts of the galaxy were moving toward or away from us, they could infer how mass was distributed and how the system was rotating. Radio astronomy, which emerged in the mid-20th century, added another powerful tool. It allowed scientists to detect the faint radio emissions from hydrogen gas throughout the galaxy, even in regions blocked by dust. These radio maps revealed long, curved features that matched what one would expect from spiral arms. The Milky Way's shape began to emerge not as a simple disk, but as a barred spiral, with a dense central region and arms that wound outward. Looking back at this long journey, it is striking how the way people imagine the Milky Way shape reflects the tools and ideas they had available at the time. When the sky was seen as a dome, the galaxy was a stripe on its surface. When stars were thought of as isolated points, the Milky Way became a collection of them, spread out in a flattened cloud. When other galaxies were discovered and studied, our own began to be understood as part of a larger family of similar structures. There is also a quieter, more human thread running through this history. At every stage, people were using what they knew best to make sense of something far beyond their direct experience. Early storytellers used familiar relationships and landscapes. Early astronomers used counting and geometry. Modern scientists use data, simulations, and instruments that can detect light our eyes will never see. Each approach builds on the last not by erasing it, but by adding another layer of understanding. Even now, the map of the Milky Way is not complete. New surveys continue to reveal streams of stars left behind by smaller galaxies that were pulled apart and absorbed over billions of years. The disk appears to ripple, as if something passed through it long ago, sending waves of motion through the stars. The halo of dark matter that surrounds the visible galaxy is still inferred rather than observed directly. Its shape and extent are subject of ongoing research. In a way, this brings us back to where we started. The Milky Way remains something that is partly seen and partly imagined. We no longer fill it with gods and mythical rivers, but we do fill it with models, simulations, and theoretical structures that help us grasp its form. The stories have changed, but the impulse behind them is the same. There is a band of light in the sky, and we want to know what it is, where it goes, and how we fit into it. As you think about this long arc from myth to map, from spilled milk to star counts to radio waves, it is worth noticing how much of the journey has depended on perspective. The Milky Way did not change shape over the course of human history. Our way of seeing it did. Each new idea, each new instrument, each new measurement shifted the mental picture a little further from the sky as a painted ceiling, and a little closer to the galaxy as a vast, rotating system of matter and energy. Begin by imagining that the Milky Way is not a distant object at all, not something hanging over you like a picture on the ceiling of the sky, but a place you are already standing in. The ground beneath your feet, the air around you, the planet carrying you through space, all of it is moving together as part of a much larger structure. This shift in perspective is subtle but important. Instead of asking what the galaxy looks like, the question becomes more personal. Where are we inside it? How far are we from the center, from the arms, from the edges? For a long time, humans assumed that whatever vast system held the stars must naturally place Earth somewhere near the center. It is a very human instinct to imagine ourselves at the middle of things. Early models of the universe reflected that assumption. Even when the idea of a galaxy full of stars began to take shape, many people still pictured the sun sitting comfortably near its heart, surrounded by layers of stars extending outward in all directions. It was only gradually and with some resistance that this idea began to change. The first major step away from a central position came in the early 20th century, when astronomers started measuring the distances to clusters of stars known as globular clusters. These are dense, spherical collections of very old stars that orbit the Milky Way far above and below its disk. By studying the distribution of these clusters in the sky, one astronomer, Harlow Shapley, noticed something intriguing. They were not centered around the sun. Instead, they seemed to cluster around a point in the direction of the constellation Sagittarius. This observation led to a quiet but profound conclusion. The center of the Milky Way was not where we are. It lay tens of thousands of light years away, in a direction that from Earth is heavily obscured by dust and gas. The sun, and with it our entire solar system, occupied a position far from the middle, out in one of the galaxy's broad sweeping arms. Today, we know that our home sits about 26,000 light-years from the galactic center. To put that into perspective, if the Milky Way were scaled down to the size of a large city, the center would be a busy downtown core, and we would be living somewhere in the suburbs, not at the edge, but certainly not near the central hub. This placement shapes everything we see when we look out into the galaxy. The region we inhabit is known as the Orion Arm, or sometimes the Orion Spur. It is not one of the Milky Way's main spiral arms. but rather a smaller bridge of stars and gas connecting two larger ones, the Perseus arm and the Sagittarius arm. Our Sun sits within this spur, surrounded by a local neighbourhood of stars that share a similar orbit around the galactic centre. This neighbourhood is often called the local bubble, a region of relatively low-density gas that is thought to have been carved out by ancient supernova explosions. Millions of years ago, massive stars in this area ended their lives in powerful blasts, pushing away much of the surrounding material and leaving behind a kind of cosmic cavity. Our solar system now drifts through this quieter patch of space, which may be one reason we have a relatively clear view of the stars around us compared to some denser regions of the galaxy. Finding our place in the Milky Way is not as simple as reading coordinates off a map. Distances on a galactic scale are notoriously difficult to measure. Astronomers rely on a combination of techniques, each suited to a different range of distances. For nearby stars, one of the most reliable methods is parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant ones. By measuring this tiny change in position, scientists can calculate how far away a star is, using geometry rather than assumptions about brightness or size. For stars farther away, other methods come into play. Certain types of stars, known as standard candles, have well understood relationships between their brightness and their intrinsic properties. By comparing how bright they appear from Earth to how bright they are known to be, astronomers can estimate their distance. One of the most famous examples of this is the Cepheid variable star, which brightens and dims in a regular pattern. The period of this variation is directly linked to its true luminosity, making it a useful marker on the cosmic distance scale. By combining these techniques, along with data from modern space missions like Gaia, which is measuring the positions and motions of over 1 billion stars, a detailed 3-dimensional map of our local region of the galaxy is gradually taking shape. This map does more than tell us where stars are. It reveals how they are moving, how they cluster, and how the disk of the Milky Way itself is subtly warped and rippled. Our Sun is not standing still in this vast system. It is in motion, orbiting the centre of the galaxy at a speed of about 220 kilometers per second. Even at that remarkable pace, it takes roughly 230 million years to complete one full orbit. This span of time is sometimes called a galactic year. If you think about the entire history of humanity, from the first stone tools to the present day, it covers only a tiny fraction of one such orbit. The Sun has made around 20 orbits since it formed, long before Earth even existed. As the Sun travels along its path, it does not follow a perfect circle. Its orbit is slightly elliptical, and it also moves up and down through the plane of the galaxy, bobbing gently like a slow cosmic wave. Over millions of years, our solar system passes through regions of higher and lower star density, through spiral arms rich in gas and dust, and into quieter interarm spaces like the one we currently occupy. This journey may have influenced the history of life on Earth in subtle ways. Some scientists have speculated that passing through denser regions of the galaxy could increase the likelihood of nearby supernova explosions or gravitational disturbances from passing stars, events that might affect the outer reaches of our solar system. While these ideas are still being studied and debated, they add another layer of connection between our planet and the larger galactic environment. When you look up at the night sky, the stars you see are not evenly scattered in all directions. Their distribution reflects our position in the galaxy. Toward the galactic centre, the sky is richer, more crowded with stars and more heavily veiled by dark clouds of dust. In the opposite direction, looking outward toward the edge of the Milky Way, the star field thins out, and the glow of the galaxy fades more quickly into darkness. This difference in appearance is one of the clues that helped astronomers determine where we are located. By mapping the brightness and density of stars across the sky, they could infer the overall structure of the disk and the direction of the central bulge. The fact that the Milky Way appears thicker and brighter in one part of the sky and thinner in another is not a random pattern. It is a perspective effect, shaped by our off-center position inside a flattened, rotating system. Another important marker of our place in the galaxy comes from radio astronomy. Clouds of hydrogen gas emit radio waves at a very specific frequency. By measuring the slight shift in this frequency caused by the motion of the gas, astronomers can determine how different parts of the galaxy are moving relative to us. This information reveals the rotation curve of the Milky Way, showing how fast material at various distances from the centre is orbiting. These rotation curves led to one of the most surprising discoveries in modern astronomy. The outer parts of the galaxy are moving much faster than they should be, if only the visible stars and gas were providing the gravitational pull. The most likely explanation is the presence of a large amount of unseen mass, what we now call dark matter, forming a vast halo around the Milky Way. This invisible structure plays a major role in shaping the galaxy and in defining the paths that stars, including our Sun, follow as they move through space. Understanding our position also means recognizing the limits of our view. The center of the Milky Way lies in a direction that is heavily obscured by dust, making it difficult to study in visible light. For much of history, this region was a mystery, a bright but indistinct glow hidden behind dark lanes. It was only with the advent of infrared and radio telescopes that astronomers could begin to peer through the dust and observe the dense star fields and energetic phenomena near the core. From our vantage point, the center of the galaxy appears in the constellation Sagittarius, which is why that part of the Milky Way often looks especially bright and detailed in the summer sky in the northern hemisphere. When you look in that direction, you are looking inward, toward the crowded heart of the system, where stars are packed more tightly and where the supermassive black hole at the core exerts its influence. Looking in the opposite direction, toward the constellation Auriga and beyond, you're gazing outward, toward the thinner, less populated regions of the disk, and eventually toward the faint edge of the galaxy. This outward view can feel quieter, less dramatic, but it is just as much a part of the Milky Way story. It shows us where the disk tapers off, where stars become fewer and the halo begins to dominate. There is something quietly striking about realizing that every star you see is part of a shared motion, all of them, including the Sun, tracing out long, slow paths around a center we cannot directly see. This shared movement ties together objects separated by thousands or tens of thousands of light years into a single, coherent system. Even though the distances are vast, the structure is real, and our place within it is not random. It is defined by gravity, by the distribution of mass, and by the long history of the galaxy's formation. The Milky Way itself did not form all at once. It grew over billions of years by drawing in smaller galaxies and clouds of gas. Some of the stars around us may not have formed in the Milky Way at all, but in smaller systems that were later absorbed. Streams of stars moving together through the halo are the remnants of these ancient mergers, stretched out by the galaxy's gravity into long, thin trails. Our position in the disk is part of this larger story of growth and change, a story written in the motions and compositions of the stars around us. Modern surveys have begun to reveal just how complex our local region is. Instead of a smooth, flat disk, the Milky Way's plane is rippled and warped. There are waves of stars moving up and down, possibly caused by past encounters with smaller galaxies or massive clouds of gas. These features suggest that the galaxy is still settling, still responding to influences both internal and external. From a human perspective, these motions are almost imperceptible. Over the course of a lifetime, the positions of the stars change only slightly. The constellations look the same generation after generation. But on the timescale of millions of years, the sky is in constant flux. Stars drift, clusters disperse, and the overall shape of the spiral arms evolves. Our place in the galaxy is not fixed in a permanent sense. It is part of a long, ongoing journey. Thinking about this can bring a different kind of awareness to the simple act of being here. The planet you're on is not just spinning and orbiting a star. It is riding along on a much larger path, carried by the motion of the sun through the Milky Way. Every moment you are moving through space at incredible speed, even if it feels like you're perfectly still. At the same time, our position is, in another sense, very ordinary. There is nothing especially unique about the Orion Spur. It is one small feature in a galaxy full of similar structures. The stars around us are a mix of different ages and types, not dramatically different from those found in many other parts of the disk. This ordinariness is perhaps part of what makes the Milky Way feel more like a home than a spectacle. We are not at the centre of things, but we are comfortably embedded in them. As this picture comes together, the shape of the Milky Way becomes more than a diagram in a textbook. It becomes a context for your own existence. The distances, the motions, the structures, all of them form a kind of cosmic address. Earth orbits the Sun. The Sun orbits the galactic centre. The Milky Way itself moves through a group of nearby galaxies, and that group is part of a larger cluster, and so on, outward into a vast network of structure that extends across the observable universe. For now, though, it is enough to stay with the scale of the galaxy itself, to let the idea of our place within it settle gently. The next time you see the Milky Way stretching across the sky, you might picture not just a band of light, but a cross-section of a huge rotating system, with you located in one of its quieter regions, looking inward toward its crowded heart and outward toward its fading edge. Turn your attention, gently and without any rush, toward a part of the sky that most of us have seen, but very few of us have truly met. This is not a direction marked by a single bright star or an obvious pattern. It is a region that hides behind layers of shadow, a place where light struggles to reach us, and where the most important features of our galaxy remain tucked away behind a veil of dust and distance. This is the direction of the Milky Way's centre, the quiet heart of the system we call home. From Earth, that centre lies in the general direction of the constellation Sagittarius. On a clear, dark summer night in the northern hemisphere, you might notice that the Milky Way looks especially thick and bright in that part of the sky, as if the glowing band has gathered itself into a dense, luminous knot. That visual impression is not misleading. When you look towards Sagittarius, you're looking inward, across tens of thousands of light years, into the most crowded and energetic region of the galaxy. Yet, despite its importance, this central zone does not reveal itself easily. The main obstacle is something both simple and pervasive: dust. Between us and the galactic centre lie enormous clouds of tiny particles, grains of carbon, silicates and frozen compounds, scattered throughout the disk of the Milky Way. These grains are very good at blocking and scattering visible light. The result is that, in ordinary optical telescopes, the central region of the galaxy appears as a confusing mix of bright star fields and dark, opaque patches. It is like trying to observe a distant city through a thick, uneven fog. You know there is something there, something large and complex, but the details remain frustratingly out of reach. For a long time, this meant that the true nature of the galaxy's core was left largely to speculation. Early astronomers could see that the star density increased dramatically in that direction, suggesting that this was where the bulk of the galaxy's mass and activity lay. But what exactly was there, and how it was structured, remained unclear. The Milky Way's heart was, in a very real sense, hidden from view. The breakthrough came when astronomers began to look beyond visible light. Light is only one small part of a much larger spectrum of electromagnetic radiation. There are radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays, each with different properties, and each able to pass through or interact with matter in different ways. Dust that blocks visible light often allows longer wavelength radiation, like infrared and radio waves, to pass through more easily. By building telescopes that could detect these other forms of light, scientists found a way to peer through the galactic fog. Infrared observations, in particular, revealed a stunningly dense and complex region at the centre of the Milky Way. Where visible light showed only a hazy glow, infrared light uncovered a packed city of stars, clusters, and swirling clouds of gas. At the very core of this region lies something even more remarkable. A supermassive black hole, known as Sagittarius A star, sits at the exact gravitational centre of the galaxy. This object has a mass about 4 million times that of the Sun, yet it occupies a region of space no larger than our solar system. It does not shine in the way stars do. Instead, it reveals itself through its influence on the matter around it. Gas and dust that stray too close are pulled in, heated to extreme temperatures, and made to emit powerful bursts of radiation before disappearing beyond the black hole's event horizon. The idea that a black hole sits at the centre of the Milky Way might sound dramatic, even violent, but the reality is, in some ways, surprisingly calm. Sagittarius A star is not currently in a highly active phase. It is not devouring vast amounts of material or blasting out enormous jets of energy. Compared to the central black holes of some other galaxies, which can outshine the combined light of all their stars, ours is relatively quiet. It is there, massive and influential, but largely content to sit and shape the motions of the stars around it. How do we know this black hole is there if we cannot see it directly? The answer lies in careful, patient observation of the stars in its immediate neighbourhood. Over the past few decades, astronomers have tracked the orbits of individual stars near the galactic centre with extraordinary precision. These stars move at incredible speeds, some completing full orbits in just a few decades. By measuring their paths, scientists can calculate the mass of the invisible object they're orbiting. The only thing that fits the data is a supermassive black hole. Surrounding this central point is a dense bulge of stars, a roughly spherical region that stands out from the flatter disk of the galaxy. This bulge is made up mostly of older stars, many of them formed early in the Milky Way's history. Their orbits are more random and less neatly aligned with the plane of the disk, giving this region a puffed-up three-dimensional shape rather than a thin, flat one. Extending through this bulge is the galactic bar, a long straight structure of stars that stretches across the centre like a luminous bridge. This bar is one of the defining features of the Milky Way's overall shape. From its ends, the spiral arms of the galaxy appear to emerge, curving outward into the disk. The bar itself is not static. It rotates, slowly but steadily, and this motion plays an important role in shaping the flow of gas and stars in the inner regions of the galaxy. Gas clouds in the disk tend to drift along the spiral arms, but when they reach the bar, their paths are altered. Some are funneled inward toward the centre, where they can trigger bursts of star formation. Others are sent outward, redistributed into different parts of the disk. In this way, the bar acts like a kind of galactic traffic controller, influencing how material moves and where new stars are likely to form. The central region is in fact one of the most active star-forming environments in the Milky Way. Dense clouds of gas and dust collapse under their own gravity, giving rise to clusters of young, massive stars. These stars burn hot and bright, emitting intense radiation and powerful stellar winds that shape their surroundings. They carve out cavities in the gas, trigger new rounds of collapse in nearby clouds, and eventually, when they reach the end of their lives, explode as supernovae, seeding the region with heavy elements. All of this activity is largely hidden from view in visible light, but in infrared and radio images it becomes a vivid and dynamic landscape. Filaments of gas twist and arc through space. Bright knots mark the locations of newborn star clusters. Shock waves ripple outward from past explosions. The quiet heart of the galaxy, it turns out, is not so quiet at all. It is a place of constant motion and change, just operating behind a curtain that keeps its drama mostly out of sight. The reason this central region matters so much to our understanding of the Milky Way's shape is that it anchors the entire system. The distribution of mass in the core, including the bulge, the bar and the black hole, determines how the rest of the galaxy rotates. stars and gas in the disk follow paths that are shaped by this central gravitational field, tracing out the spiral pattern we see on a larger scale. By studying the motions of stars near the centre and farther out in the disk, astronomers can build a picture of how mass is spread throughout the galaxy. This, in turn, reveals the presence of the dark matter halo that extends far beyond the visible stars. The behaviour of the inner regions is a key piece of this puzzle, because it provides a reference point for the entire rotation curve of the Milky Way. There is also a historical dimension to this region. The stars in the central bulge are on average older and richer in heavy elements than many of those in the outer disk. This suggests that the core of the galaxy formed early and rapidly, gathering material and forming stars at a high rate in the Milky Way's youth. Over time, the disk grew outward, fed by infalling gas and by the gradual merging of smaller systems. Some of the stars near the centre may even be remnants of ancient galaxies that were absorbed long ago. Their motions and chemical compositions carry clues to these long-past events, like a kind of fossil record written in light. By decoding these clues, astronomers can reconstruct the Milky Way's formation history, piecing together how a collection of smaller structures became the large barred spiral we see today. From our position in the disk, this central region is both close, in a cosmic sense, and profoundly distant. 26,000 light-years is not far compared to the size of the observable universe, but it is far enough that everything we see from there is already a glimpse into the past. The light reaching your eyes tonight left the stars near the galactic centre tens of thousands of years ago, long before the first cities rose on Earth, long before recorded history. In that sense, looking toward the heart of the Milky Way is also looking backward in time. There is something quietly humbling about that. The core of the galaxy has been there, shaping the paths of stars and gas, long before our planet formed. It will continue to be there long after the sun has exhausted its fuel and the continents on Earth have shifted into new arrangements. The timescales involved make individual human lives feel like brief moments in a much longer story. At the same time, our ability to study this region at all is a testament to how far our tools and methods have come. We have built instruments that can detect tiny shifts in starlight, measure the motion of stars across the sky to a fraction of a millisecond, and capture the faint glow of gas hidden behind clouds of dust. We have even produced an image of the shadow of a black hole, using a network of telescopes spread across the Earth to create a virtual instrument the size of a planet. While that particular image was of a black hole in a different galaxy, the same techniques are being used to probe Sagittarius A star itself. These efforts are not just about satisfying curiosity. They help refine our understanding of fundamental physics, from how gravity behaves in extreme environments to how matter and energy interact under intense conditions. The centre of the Milky Way is, in a sense, a natural laboratory, offering a chance to test ideas that cannot be explored on Earth. There is also a quieter, more personal aspect to this exploration. Knowing that there is a dense, dynamic, hidden region at the heart of the galaxy adds depth to the simple image of the Milky Way as a band of light in the sky. It reminds us that what we see is only a surface, a cross-section through a much more complex structure. Behind the glow and the shadows lies a crowded, energetic core that plays a central role in shaping the entire system. When you look towards Sagittarius on a dark night, you're not just seeing a brighter patch of sky. You're looking in the direction of a supermassive black hole, of vast star clusters, of swirling clouds of gas, and of a bar of stars stretching across the galaxy's middle. All of that is compressed into a soft, hazy glow by distance and dust, a quiet reminder of how much is hidden within even the most familiar sights. As this picture settles in, it becomes easier to understand the Milky Way not as a flat picture, but as a layered three-dimensional structure. There is a disk, a bulge, a bar, a halo, and at the very centre a compact massive object that ties it all together through gravity. Each of these components contributes to the galaxy's overall shape, and each interacts with the others in ways that are still being studied. Let your attention drift outward from the dense hidden centre of the Milky Way, away from the crowded star fields and the quiet pull of the black hole at the core, and imagine yourself moving along one of the great sweeping paths that define the galaxy's overall form. These are the spiral arms, the long curved regions of stars, gas and dust that give the Milky Way its pinwheel-like appearance when seen from afar. From our position inside the disk, we do not see them as neat, elegant arcs. We experience them instead as a series of brighter patches, darker lanes, and subtle patterns that stretch across the sky and through our local neighbourhood in space. The idea of spiral arms can sound simple at first, like decorative features painted onto a flat disk of stars. In reality, they are dynamic, complex structures shaped by motion, gravity, and the slow flow of matter through the galaxy. They are not rigid arms made of the same stars forever, rotating as a solid piece. Instead, they are more like traffic patterns, regions where material tends to gather and move in a coordinated way, creating the impression of a long-lasting structure even as individual stars and clouds pass through. To understand what these arms really are, it helps to think about the Milky Way as a rotating system. Every star, including our Sun, is orbiting the centre of the galaxy. The closer a star is to the centre, the faster it tends to move, while stars farther out move more slowly. This difference in speed, called differential rotation, means that the disk of the galaxy is constantly being sheared and stretched. If the spiral arms were made of a fixed set of stars, this shearing would quickly wind them up into a tight, messy coil. The fact that we still see broad, open spirals suggests that something else is going on. One of the leading ideas is known as density wave theory. According to this model, the spiral arms are not made of a permanent group of stars, but are instead regions of higher density that move through the disk like a slow-moving wave. As gas and stars orbit the centre of the galaxy, they enter these denser regions, slow down slightly due to the increased gravitational pull, and then move on, leaving the region behind. The wave itself persists, even though the material within it is constantly changing. This process has an important side effect. When clouds of gas enter a spiral arm, they are compressed. This compression can trigger the collapse of parts of the cloud, leading to the formation of new stars. The most massive of these newborn stars burn very hot and very bright, but they do not live long. They shine intensely for a few million years and then end their lives in supernova explosions. Because of their short lifespans, they do not have time to drift far from the place where they formed. The result is that spiral arms tend to be lined with bright blue stars and glowing clouds of gas, making them stand out against the older, redder stars in the rest of the disk. From Earth, this pattern shows up as brighter sections of the Milky Way, often marked by star clusters and regions of glowing gas. If you look at long exposure photographs of the night sky, you can sometimes see these star-forming regions as faint reddish patches along the band of the galaxy. These are places where hydrogen gas is being energized by nearby hot stars, causing it to emit light at specific wavelengths. The Milky Way has several major spiral arms, though their exact number and shape are still subjects of active research. The main ones are known as the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm. In addition to these, there are smaller features, like the Orion Spur where our own solar system is located. These arms are not evenly spaced or perfectly symmetric. They vary in thickness, brightness, and how clearly they can be traced, reflecting the uneven distribution of gas and stars throughout the disk. Mapping these arms from within is a challenging task. Dust obscures large portions of the galaxy in visible light, especially in the inner regions. This is where radio and infrared observations become especially valuable. Hydrogen gas, which is abundant in the spiral arms, emits radio waves at a characteristic frequency. By measuring this emission and tracking how it shifts due to the motion of the gas, astronomers can trace the large-scale structure of the arms even in regions hidden by dust. Infrared light, which can pass through dust more easily than visible light, reveals the distribution of older stars in the disk. By combining these different views, scientists can build a more complete picture of where the arms are and how they curve around the centre of the galaxy. One of the striking features revealed by these maps is that the spiral arms are not perfectly smooth. They contain branches, spurs, and irregularities, like a network of side roads branching off from a main highway. These features can form when local gravitational effects, supernova explosions, or interactions with nearby structures disturb the flow of gas and stars. Over time, some of these side features may grow into more prominent arms, while others fade away. The arms are also not static over long periods. The overall pattern can change as the galaxy evolves. Interactions with smaller galaxies, such as the Large and Small Magellanic Clouds, can tug on the Milky Way's disk, creating ripples and warps that influence the shape and position of the spiral arms. Streams of stars from past mergers can weave through the disk, adding complexity to the pattern. Our own position in the Orion Spur gives us a particular perspective on all of this. We are located between two of the major arms, in a region that is not as densely packed with gas and young stars as the main arms themselves. This can make it harder to see the full sweep of the spiral pattern from our vantage point. Instead of a clear continuous curve, we see segments and hints, pieces of the larger design scattered across the sky. Even so, there are moments when the structure becomes more apparent. When you look toward the Sagittarius arm, in the direction of the galactic centre, the Milky Way often appears especially bright and rich in detail. This is because you're looking along a major spiral arm, where star formation is active and the density of stars is high. In the opposite direction, toward the outer parts of the galaxy, the band of light thins out, reflecting the lower density of stars and gas in those regions. The presence of dark dust lanes along the arms adds another layer of texture to this view. These lanes are made of dense clouds of dust that run alongside the star-forming regions. They can appear as sharp, winding shadows against the brighter background of stars. In some cases, they trace the inner edges of spiral arms, marking the places where gas is being compressed and stars are beginning to form. From a physical standpoint, these dust lanes are part of a larger cycle of matter in the galaxy. Gas flows into the spiral arms, forms stars, and is then returned to the interstellar medium through stellar winds and supernova explosions. This enriched material can later be incorporated into new generations of stars and planets. The spiral arms, in this sense, are not just structural features. They are sites of ongoing creation and recycling, where the raw ingredients of the galaxy are continually reshaped. The connection between spiral arms and star formation has important implications for the overall appearance of the Milky Way. The arms tend to be more prominent in younger, bluer light, while the underlying disk of older stars gives the galaxy its broader, smoother glow. This combination of a structured, active pattern overlaid on a more diffuse background is what gives spiral galaxies their distinctive look. When astronomers study other galaxies, they see a wide variety of spiral forms. Some have tightly wound arms that wrap closely around the centre. Others have loose, open spirals with large gaps between the arms. Some show a strong central bar like the Milky Way, while others do not. By comparing these different systems, scientists can learn more about the factors that influence spiral structure, such as the amount of gas in the disk, the mass of the central bulge, and the presence of nearby galaxies. These comparisons also help refine our understanding of our own galaxy. For example, observations of external galaxies suggest that the Milky Way's arms may be less sharply defined than those of some classic grand design spirals like the Whirlpool Galaxy. Instead, our galaxy may be more of a flocculent spiral, with arms that are patchy and segmented rather than continuous and smooth. This fits with what we see from within, where the pattern appears as a series of bright and dark regions rather than a single, clear curve. The motion of stars through the spiral arms adds another layer of subtlety to the picture. As a star orbits the centre of the galaxy, it may pass through several arms over the course of a galactic year. The Sun itself has likely crossed spiral arms multiple times in its history. Each crossing would have brought it into regions of higher gas density and increased star formation activity. Some researchers have explored the idea that these passages could be linked to changes in the solar system's environment, such as variations in the rate of nearby supernovae or the amount of cosmic radiation reaching Earth. While these connections are still being studied, they highlight the idea that the spiral arms are not just distant features to be admired. They are part of the environment through which our solar system moves, shaping the broader conditions of our corner of the galaxy over long periods of time. There is also a sense in which the arms help define the Milky Way's identity. The spiral pattern is one of the most recognizable features of our galaxy, a kind of signature that places it within a larger family of similar systems. When you see images of distant spirals with their glowing arms and dark lanes, you're looking at structures that share a common design with the one you inhabit, even if the details differ. From our internal viewpoint, this shared design can be easy to forget. The Milky Way, seen from Earth, is a band of light, not a pinwheel. The arms are not obvious curves in the sky, but subtle variations in brightness and texture. It takes a combination of careful observation, sophisticated instruments, and a bit of imagination to connect that hazy ribbon overhead to the grand spiral form revealed in images of other galaxies. That act of connection, of linking the familiar view from the ground to the larger structure inferred from data, is a recurring theme in our understanding of the Milky Way. We start with what we can see and feel, and then we extend that picture outward, using physics and mathematics to fill in the parts that are hidden. The spiral arms are a perfect example of this process. They are both visible and invisible, both present in the night sky and revealed only through careful analysis. There is something quietly satisfying about realizing that the bright patch of the Milky Way you notice on a summer night is not just a random cluster of stars, but part of a sweeping, organized pattern that wraps around the entire galaxy, that the dark lane cutting through it is not a gap, but a dense cloud where new stars may be forming, that the faint glow stretching off toward the horizon is the combined light of stars in an arm that curves around a center you cannot see. The shape of the Milky Way begins to feel less like an abstract diagram and more like a place with structure and flow. The arms are pathways, not in the sense of roads you could travel, but in the sense of regions that guide the movement of matter and the cycle of starbirth and death. They give the galaxy its rhythm, its pattern, its slow, graceful motion through cosmic time. Somewhere deep within the glow and shadow of the Milky Way's center, hidden behind layers of dust and distance, lies a structure that quietly reshapes how the entire galaxy moves. It is not a bright ring or a simple cluster of stars. It is a long, dense band stretching across the heart of the system like a luminous bridge, connecting one side of the galaxy to the other. This is the galactic bar, a feature that for much of human history went unnoticed, not because it was small, but because it was perfectly placed to hide from our view. The idea that our galaxy might have a bar running through its middle is a relatively recent one in astronomical terms. For a long time, astronomers pictured the Milky Way as a straightforward spiral, with arms curving gracefully out from a rounded central bulge. That image was based partly on what could be seen in other galaxies and partly on the limited information available from within our own. The centre of the Milky Way, after all, is one of the most difficult regions of the sky to study in visible light. Thick clouds of dust block the view, and the sheer density of stars makes it hard to separate individual features. As technology improved and astronomers began to observe the galaxy in infrared and radio wavelengths, a different picture started to emerge. Instead of a simple round core, the distribution of stars near the centre appeared elongated. There was a noticeable stretching of the central region, a subtle but consistent sign that the Milky Way's heart was not perfectly symmetrical. Over time, as more data accumulated, this elongation resolved into something more defined. the galaxy was not just a spiral, it was a barred spiral, with a central bar of stars extending across its core. From a distance, barred spiral galaxies are easy to recognize. The bar appears as a bright straight line cutting through the center, with spiral arms unfurling from its ends rather than directly from the core. When you look at images of galaxies like NGC 1300 or the nearby Andromeda galaxy, the pattern is clear. The Milky Way, however, does not offer us that luxury. We cannot step back and take a picture. We have to infer the bar's existence and shape from the motions and positions of stars, gas and dust, all seen from a point embedded within the disk. One of the earliest hints came from the way stars near the centre of the galaxy move. Instead of orbiting in neat circular paths around the core, many of them follow elongated orbits, aligned along a common direction. This kind of motion is exactly what you would expect if there were a bar-shaped mass dominating the gravitational field in that region. The stars are not just responding to a central point of gravity, but to an extended structure that pulls more strongly along one axis than another. Infrared surveys added further support. When astronomers mapped the brightness of stars across the central region in infrared light, which can penetrate dust more effectively than visible light, they found a clear, elongated distribution. The bar appeared to be about 27,000 light-years long, stretching across the inner disk of the galaxy at a slight angle relative to the line between the Sun and the galactic centre. From our perspective, this means we are looking at the bar somewhat from the side rather than straight on, which helps explain why it took so long to recognise. The bar's orientation is an important detail. It is not aligned directly with our line of sight to the centre. Instead, it is tilted, so that one end is closer to us than the other. This tilt creates subtle asymmetries in the brightness and distribution of stars we see in different parts of the inner Milky Way. By carefully measuring these differences, astronomers have been able to estimate the bar's angle and length, building a three-dimensional picture of its shape. Understanding the bar is not just a matter of labelling a feature on a map. It has a profound influence on how the galaxy works. The bar acts as a kind of engine, redistributing material within the disk. As the bar rotates, it creates gravitational forces that can push gas inward toward the centre or outward toward the spiral arms. This movement of gas plays a key role in regulating where and when new stars form. In many barred spiral galaxies, the central region shows signs of enhanced star formation. Gas funneled along the bar can accumulate near the core, building up dense clouds that collapse to form new stars. The Milky Way is no exception. The inner few thousand light-years of the galaxy contain massive star-forming regions, packed with young, hot stars and complex networks of gas and dust. These regions are energetic and dynamic, shaped by the combined effects of gravity, radiation, and the explosive ends of massive stars. At the same time, the bar can also act as a kind of barrier. In some cases, it can slow the inward flow of gas, creating rings of star formation at certain distances from the centre. These rings are seen in other galaxies and may exist in our own as well, though their exact structure is still being studied. The interplay between the bar and the spiral arms creates a pattern of movement that is both organised and constantly changing. The bar itself is made up mostly of older stars, similar to those found in the central bulge. These stars tend to have lower amounts of heavy elements compared to younger stars in the disk, suggesting they formed early in the galaxy's history. This has led to questions about how the bar formed in the first place. Did it emerge early on as part of the galaxy's initial structure, or did it develop later as the disk evolved and became unstable? Computer simulations offer some insight. In many models, a rotating disk of stars and gas can naturally develop a bar over time. Small irregularities in the disk can grow under the influence of gravity, eventually forming a large, elongated structure. Once established, the bar can persist for billions of years, shaping the evolution of the galaxy as it rotates. These simulations also suggest that bars are not permanent features in all cases. They can weaken or even dissolve under certain conditions, such as interactions with other galaxies or changes in the distribution of mass within the disk. This raises the possibility that the Milky Way's bar has a history of its own, perhaps forming, changing and stabilizing over the course of the galaxy's long life. The rotation of the bar is another key piece of the puzzle. The bar does not spin at the same rate as the stars in the disk. It has its own pattern speed, a measure of how fast the bar structure itself rotates. This difference in speed creates regions where the motion of stars and gas resonates with the bar's rotation, leading to complex orbital patterns and influencing the overall shape of the spiral arms. These resonances can be thought of as cosmic meeting points, places where the gravitational effects of the bar and the orbital motion of material in the disk line up in a particular way. At these locations, gas can pile up, stars can be scattered into new orbits, and the structure of the galaxy can be subtly reshaped. Over long periods of time, these processes can have a significant impact on the distribution of stars and the appearance of the Milky Way's inner regions. From our position in the Orion Spur, the effects of the bar are not directly visible in the night sky. We cannot see a straight line of stars cutting across the Milky Way's centre. What we see instead are indirect signs, variations in the density of stars, the distribution of gas, and the motions of objects in the inner disk. It is through careful analysis of these patterns that the presence and properties of the bar are revealed. One of the more intriguing discoveries in recent years is the shape of the central bulge itself. Instead of being a simple, rounded cluster of stars, the bulge appears to have a boxy or even peanut-like shape when viewed from certain angles. This unusual form is thought to be related to the bar. As the bar evolves, it can cause stars to move out of the plane of the disk, creating a thickened three-dimensional structure that gives the bulge its distinctive appearance. This connection between the bar and the bulge highlights how closely linked the different parts of the galaxy are. The Milky Way is not a collection of independent components. It is a single, interacting system, where changes in one region can ripple outward and influence the whole. The bar is both a product of this system and a driver of its ongoing evolution. There is also a broader context to consider. Bars are common in spiral galaxies. Surveys of the nearby universe suggest that a large fraction of spiral galaxies, perhaps more than half, have some form of central bar. This raises interesting questions about why bars form and what role they play in galactic life cycles. Are they a natural stage in the evolution of most disk galaxies? Do they help regulate star formation and the growth of central black holes? Or are they more like temporary features, appearing and disappearing as conditions change? In the case of the Milky Way, the presence of a bar may be linked to the relatively quiet state of Sagittarius A star, the supermassive black hole at the centre. By controlling the flow of gas into the inner regions, the bar could influence how much material reaches the black hole, and therefore how active it becomes. In galaxies with very active central black holes, known as active galactic nuclei, the relationship between bars and black hole feeding is an area of active research. From a more human perspective, the bar adds another layer of depth to the idea of the Milky Way's shape. It means that our galaxy is not just a simple pinwheel, but a more complex structure, with a straight, elongated core and curved arms extending outward. This combination of straight lines and sweeping curves gives the galaxy a kind of internal tension, a balance between order and motion that plays out over billions of years. It also means that when you look toward the bright, crowded region of the Milky Way in the summer sky, you are not just seeing a dense cluster of stars. You're looking in the direction of one end of this vast central bridge of stars. The light reaching your eyes has travelled across a structure tens of thousands of light years long, shaped by gravity and motion on a scale that is difficult to fully grasp. The process of uncovering the bar's existence is a good example of how our understanding of the galaxy often advances. It is not usually a single dramatic discovery, but a gradual accumulation of evidence from many different sources. Star counts, infrared surveys, measurements of stellar motion, computer simulations, and comparisons with other galaxies all contribute pieces to the puzzle. Over time, these pieces fit together into a coherent picture that reveals a feature that was always there, quietly shaping the galaxy from within. As more data become available, that picture continues to be refined. New surveys are mapping the inner regions of the Milky Way in unprecedented detail, tracking the motions of millions of stars and revealing subtle patterns in their orbits. These patterns offer clues about the bar's strength, its rotation rate, and its influence on the surrounding disk. Each new result adds a bit more clarity to our mental map of the galaxy's core. There is a certain elegance in the idea that a structure so large and influential can remain hidden in plain sight for so long. The bar is not invisible, but it is perfectly positioned to blend into the dense, dusty, star-filled background of the galactic centre. It takes a combination of technology, patience, and perspective to tease it out of the data and recognise it for what it is. Thinking about this can change how the Milky Way feels as a concept. It is no longer just a distant, abstract spiral. It is a system with internal architecture, with beams and bridges of stars, with flows of gas guided along invisible gravitational channels. The bar is one of those channels, a structural feature that links the quiet heart of the galaxy to the sweeping arms that define its outer shape. As this understanding settles in, it naturally leads to a broader question. If so much of the Milky Way structure is defined by features we cannot easily see, what else lies beyond the bright disk and the obvious arms? Between you and the farthest stars of the Milky Way lies a quiet, complicated veil, one that turns a simple act of looking into a long exercise in patience and interpretation. This veil is not a single thing, but a mixture of tiny particles, thin gas, scattered light, and the limits of human senses and instruments. It is the reason the galaxy never presents itself as a clear, complete picture. Instead, it offers fragments, hints, and softened outlines, leaving the full shape to be assembled piece by careful piece. At the most basic level, the difficulty begins with dust. Interstellar dust is made of microscopic grains, often smaller than a fraction of a human hair, composed of carbon, silicates, ice, and other compounds, forged in the outer layers of old stars and in the aftermath of stellar explosions. These grains drift through the space between stars, sometimes spread thinly, sometimes gathered into thick, cold clouds. Although each grain is tiny, together they form structures large enough to block and scatter enormous amounts of light. When visible light from a distant star or a faraway region of the galaxy encounters one of these dust clouds, much of it never makes it to your eyes or to a telescope. Some of the light is absorbed, heating the dust slightly. Some is scattered in different directions, redirected away from the line of sight. The result is extinction, a dimming of the background and reddening, a change in colour. Blue light, which has a shorter wavelength, is scattered more easily than red light, so stars seen through dust often appear redder than they really are. This effect is subtle for nearby objects and dramatic for distant ones, especially toward the dense inner regions of the Milky Way. From Earth, this means that large portions of the galaxy are hidden behind dark lanes and patches that look, at first glance, like empty spaces. In reality, these are often some of the richest and most active regions, filled with cold gas and dust that serve as the raw material for future generations of stars. The irony is that the very places where new stars are forming are also the places that are hardest to observe in ordinary light. Long before astronomers understood what these shadows were, they puzzled over their presence. Early star maps showed irregular gaps and winding dark shapes cutting through the bright band of the Milky Way. Some thought these were true voids, regions where stars simply did not exist. It took careful study and the development of new observational techniques to reveal that these were not holes in the galaxy, but clouds within it. The first big shift came with the use of photography. Long exposure images captured faint stars and subtle variations in brightness, that the human eye could not hold on to in real time. These photographs made the dark lanes stand out more clearly, highlighting their complex branching forms. Astronomers began to suspect that something in the foreground was blocking the light from behind rather than the background simply being empty. The next leap forward came with infrared astronomy. Infrared light has a longer wavelength than visible light, which allows it to pass through dust more easily. When telescopes sensitive to infrared radiation were turned toward the Milky Way, regions that looked dark and opaque in visible images suddenly lit up with hidden stars and glowing clouds. It was as if someone had lifted a curtain, revealing a second version of the galaxy layered behind the first. This ability to see in different wavelengths is one of the most powerful tools astronomers have for building a complete picture of the Milky Way. Each part of the electromagnetic spectrum tells a different story. Radio waves trace cold hydrogen gas and large-scale structure. Infrared light reveals warm dust and young stars still wrapped in their birth clouds. Visible light shows mature stars and glowing nebulae. Ultraviolet and X-rays highlight hot, energetic processes such as massive stars, supernova remnants, and material falling toward black holes. By combining these views, scientists can create a kind of multi-layered map, where each wavelength adds a new dimension. It's not unlike listening to an orchestra where different instruments come in and out. If you only hear the strings, you miss the brass. If you only hear the percussion, you miss the melody. To understand the full piece, you need all of them together. Even with this approach, some challenges remain stubbornly in place. One of them is simply distance. The Milky Way is enormous, stretching over 100,000 light-years from one edge of the disk to the other. Objects on the far side of the galaxy are not only dimmed by dust, but also by sheer remoteness. Light spreads out as it travels, and by the time it reaches us from the other side of the galaxy, it is faint, even if it began its journey as a powerful burst. This faintness makes it difficult to measure distances accurately. Many of the techniques astronomers use to gauge how far away something is depend on being able to measure its brightness precisely. If dust and distance both affect that brightness, it becomes harder to tell whether an object is genuinely dim and nearby or bright and far away. Untangling these factors requires careful calibration and often multiple, independent methods. Another layer of difficulty comes from our own position inside the galaxy. If you were trying to draw a map of a forest while standing among the trees, your view would be limited by trunks, branches, and undergrowth in every direction. You might see clearings here and there, and you could infer the general shape of the forest by walking around and comparing what you see, but you would never have the simple, overhead view that a bird might enjoy. This is exactly the situation we're in with the Milky Way. We cannot step outside the disk and take a picture. Every observation is made from within, looking through layers of stars, gas, and dust. This makes it hard to separate what is nearby from what is far away, and to tell whether a bright patch is a dense cluster close to us, or a larger, more distant structure seen through a thinner region of dust. Motion adds another complication. Stars and gas in the Milky Way are not standing still. They are orbiting the centre, moving at different speeds depending on their distance and the distribution of mass around them. When astronomers measure the motion of gas using radio waves, they see shifts in frequency caused by the Doppler effect. These shifts can be used to estimate how fast the gas is moving toward or away from us, and from that, infer where it is in the galaxy. This method works well in many cases, but it relies on a model of how the galaxy rotates. If that model is slightly off, the inferred distances can be wrong. In the inner parts of the galaxy, where orbits are more complex and influenced by the central bar and bulge, this approach becomes especially tricky. Different regions can share similar velocities even if they are at different distances, leading to what astronomers call distance ambiguities. Then there is the matter of scale. Some of the most important features of the Milky Way structure, such as the spiral arms, are defined by subtle, large-scale patterns rather than sharp boundaries. An arm is not a solid wall of stars. It is a region where stars and gas are slightly more concentrated than in the surrounding disk. From within, this difference can be hard to detect, especially when local variations like star clusters and individual clouds create their own patterns on smaller scales. The same is true for the galaxy's outer regions. The visible disk fades gradually into the halo, a vast faint envelope of stars and dark matter that extends far beyond what can be easily observed. There is no clear edge, no bright line where the galaxy ends and empty space begins. Instead, the density of stars simply decreases, becoming sparser and sparser until individual objects are separated by enormous distances. Detecting this halo is a challenge in itself. The stars that inhabit it are few and far between, and many of them are very old and faint. Identifying them requires deep surveys and careful analysis to distinguish them from closer stars in the disk. Streams of stars left behind by smaller galaxies that were torn apart by the Milky Way's gravity add another layer of complexity, weaving through the halo in long, thin arcs that can be hard to trace against the background. There is also the presence of something that cannot be seen at all, at least not directly. Dark matter, which makes up a large fraction of the galaxy's mass, does not emit or absorb light. Its presence is inferred from its gravitational effects on the motion of stars and gas. This means that a significant part of the Milky Way's true shape is defined by something invisible, something that can only be mapped through its influence rather than its appearance. When astronomers build models of the galaxy, they have to account for this unseen component. The rotation of the disk, the stability of the spiral arms, and the behavior of stars in the halo all point to a massive extended dark matter structure surrounding the visible galaxy. This halo likely extends far beyond the outermost stars we can detect, giving the Milky Way a gravitational footprint much larger than its luminous one. Another obstacle to seeing the whole galaxy clearly is time. Because light takes time to travel, every observation is a look into the past. When you observe a star 1,000 light-years away, you're seeing it as it was 1,000 years ago. When you observe a region near the galactic centre, you are seeing it as it was tens of thousands of years ago. This is not a problem in itself, but it means that different parts of the galaxy are being observed at slightly different moments in their history. For most large-scale structures, these time differences are small compared to the timescales over which the galaxy changes. But for energetic events, like supernova explosions or flares from the central black hole, timing can matter. Putting together a complete picture of what is happening across the galaxy at any given moment requires careful coordination of observations made in different wavelengths and at different times. Human limitations also play a role. Our eyes evolved to see a narrow range of light, and our brains are wired to recognize patterns on familiar scales. The structures of the Milky Way, from spiral arms to the halo, exist on scales so vast that they resist intuitive understanding. We rely on diagrams, simulations, and analogies to make sense of them, translating data into images and models that fit into our mental frameworks. These translations, while useful, can sometimes create a false sense of clarity. A neat, colourful picture of a spiral galaxy can make it seem as though we have a complete settled understanding of its shape. In reality, many details are still uncertain. The exact number and arrangement of the Milky Way's spiral arms, the precise size and shape of its bar, the extent and structure of its halo, and the distribution of dark matter are all active areas of research. Every new survey adds more data but also more complexity. The Gaia mission, for example, has revealed that the disk of the Milky Way is not flat but warped and rippled. There are waves of stars moving up and down, possibly caused by past interactions with smaller galaxies. These ripples complicate the simple picture of a thin, smooth disk and add another layer of challenge to mapping the galaxy's true shape. Even the stars themselves can be deceptive. Many stars are part of multiple systems, orbiting one or more companions. Some are variable, changing in brightness over time. Others are surrounded by disks of dust or envelopes of gas that affect how they appear. All of these factors have to be taken into account when using stars as markers to trace the structure of the galaxy. There is also the problem of sheer volume. The Milky Way contains hundreds of billions of stars. Mapping even a fraction of them in 3 dimensions is a monumental task. Each measurement of position, distance, and motion comes with an uncertainty, and those uncertainties add up. Creating a coherent, large-scale map from this sea of data requires sophisticated statistical methods and powerful computers. Despite all of these challenges, progress continues. Radio telescopes map the distribution of hydrogen across the disk, revealing the large-scale pattern of spiral arms. Infrared surveys chart the positions of stars in the bulge and bar, cutting through the dust that blocks visible light. Space missions measure the tiny shifts in star positions that reveal their distances and motions. Together, these efforts slowly fill in the gaps, turning shadows into structures and faint glows into defined features. There is a quiet satisfaction in this process. It is not a sudden unveiling, not a moment where the galaxy's full shape is revealed in a single dramatic image. It is a gradual assembly, like putting together a puzzle where many of the pieces are translucent and some are missing altogether. Each new piece changes the picture slightly, refining the edges and sometimes reshaping the whole. From a personal perspective, this difficulty in seeing the whole galaxy can make the act of looking up feel more meaningful. The Milky Way in the sky is not a complete story, it is an invitation. The bright band and the dark lanes are hints of something larger, deeper, and more complex than what the eye can capture. They point toward a structure that extends far beyond the limits of vision, shaped by forces and components that are only partly understood. As the picture of the Milky Way grows more detailed, it also grows more layered. Light and shadow, visible and invisible, near and far, all overlap in a way that resists simple boundaries. The galaxy's shape is not just a matter of stars arranged in a spiral. It is the result of dust clouds drifting, gas flowing, stars being born and dying, and dark matter quietly shaping the motion of everything else. Letting that complexity settle in can change how the night sky feels. The faint glow overhead becomes not just a collection of distant suns, but a surface hint of a vast structured system that you are embedded in, moving with and contributing to simply by being made of the same material. The difficulty of seeing the whole galaxy is, in a sense, a reflection of our place within it. We are part of the thing we are trying to understand. Numbers in this story are not cold or distant things. They are the gentle stepping stones that let us cross from what we can see to what we can only imagine. When astronomers talk about measuring the Milky Way, they are not laying out a ruler across the sky. They are building a bridge between tiny shifts of light in a telescope and a structure that spans 100,000 light-years. From inside the galaxy, every estimate, every calculation, and every map begins with the same quiet challenge. How do you trace the outline of a place when you cannot step outside of it? The first tool in this effort is geometry, the same simple logic that helps you judge how far away a tree is by comparing it to something closer. Astronomers call this method parallax. As Earth moves around the Sun, nearby stars appear to shift slightly against the background of more distant ones. The effect is tiny, often less than the width of a human hair held at arm's length, but it is real and measurable. By tracking this shift over the course of a year, scientists can calculate the distance to those stars using basic trigonometry. This technique forms the foundation of the entire cosmic distance scale. For stars within a few thousand light-years, parallax provides a reliable anchor. It does not depend on assumptions about how bright a star is or what kind of object it might be. It relies only on geometry and careful measurement. Space missions like Gaia have taken this method to an extraordinary level of precision, charting the positions and distances of over 1 billion stars. The result is a 3-dimensional map of our local region of the Milky Way, revealing clusters, streams, and subtle ripples in the disk that were invisible before. Yet, even this remarkable achievement has its limits. Parallax becomes harder to measure as distance increases. Beyond a certain point, the shift is simply too small to detect accurately, even with the best instruments. To reach farther into the galaxy, astronomers need other tools, ones that rely on the intrinsic properties of stars themselves. This is where standard candles come in. A standard candle is an object whose true brightness is known, or can be determined from some other measurable feature. If you know how bright something really is, and you measure how bright it appears from Earth, you can calculate how far away it must be. It is the same logic you might use to judge the distance of a street lamp at night. If it looks faint, and you know how bright those lamps usually are, you can infer that it must be far away. One of the most important types of standard candle is the Cepheid variable star. These stars brighten and dim in a regular repeating pattern. The key detail is that the period of this variation is directly related to the star's true luminosity. By observing how long it takes for a Cepheid to complete a cycle of brightening and dimming, astronomers can determine how bright it really is, and from that how far away it must be. Cepheids have been used to measure distances across the Milky Way and beyond, helping to establish the scale of the galaxy and its place in the wider universe. They act like signposts, marking out the spiral arms and tracing the distribution of stars across the disk. Other types of standard candles, such as certain kinds of supernovae and red giant stars, extend this reach even further, allowing astronomers to probe the outer regions of the galaxy and the halo beyond. Light, however, is not the only messenger. Motion carries information too. Everything in the Milky Way is moving, stars, gas and dust, all orbiting the galactic centre under the influence of gravity. By measuring how fast objects are moving toward or away from us, astronomers can infer where they are in the galaxy and how mass is distributed throughout it. This is done using the Doppler effect, the same phenomenon that makes a siren sound higher pitched as it approaches and lower pitched as it moves away. In astronomy, this effect shows up as a shift in the wavelengths of light or radio waves emitted by an object. When a cloud of gas is moving toward us, its signal is shifted slightly toward shorter wavelengths. When it is moving away, the signal shifts toward longer wavelengths. Hydrogen gas, which is abundant in the Milky Way, emits radio waves at a very specific frequency. By mapping this emission across the sky, and measuring how it shifts in different directions, astronomers can build a picture of how the gas in the galaxy is moving. From this, they can infer the rotation of the Milky Way and trace the locations of spiral arms and other large-scale structures. This method has been especially useful for studying regions hidden by dust, where visible light cannot reach. Radio waves pass through dust more easily, allowing scientists to see into the crowded inner parts of the galaxy and out toward the faint edges of the disk. The resulting maps reveal sweeping patterns of gas that curve around the center, outlining the spiral structure in a way that complements the star-based maps built from optical and infrared data. Even with these tools, there are still ambiguities. In the inner galaxy, different locations can share similar velocities, making it difficult to determine exactly how far away a particular cloud or star is. Astronomers address this by combining multiple methods, cross-checking distances estimated from motion with those derived from standard candles and parallax. Each technique has its strengths and weaknesses, and it is the overlap between them that builds confidence in the final picture. Another important approach involves star clusters. Clusters are groups of stars that form together and remain loosely bound by gravity. Because the stars in a cluster share a common origin, they often have similar ages and compositions. By studying the brightness and colour of stars in a cluster, astronomers can estimate the cluster's distance and age. Mapping the locations of clusters across the Milky Way helps trace the spiral arms and the distribution of star-forming regions. Globular clusters, which are older and found mostly in the halo, provide clues about the overall size and shape of the galaxy's extended structure. Open clusters, which are younger and found in the disk, mark out the locations of recent star formation and the paths of the spiral arms. Together they act like a set of reference points scattered throughout the system. Modern astronomy also relies heavily on spectroscopy, the study of how light is split into its component colours. Each element produces a unique pattern of lines in a spectrum like a fingerprint. By analysing these patterns, scientists can determine the composition, temperature, and motion of stars and gas. This information adds another layer to the map, revealing not just where things are, but what they are made of and how they are moving through the galaxy. Chemical composition in particular can act as a kind of historical record. Stars closer to the centre of the Milky Way tend to have higher concentrations of heavy elements, reflecting the fact that many generations of stars have lived and died there, enriching the surrounding material. Farther out in the disk and into the halo, stars are often more chemically primitive. By mapping these variations, astronomers can trace the galaxy's growth over time and identify regions that formed at different stages of its history. Computer simulations play a growing role in this process as well. By modelling how a galaxy like the Milky Way might evolve under different conditions, scientists can compare the results of their simulations to the patterns they observe in real data. If a model produces spiral arms, a bar, and a halo that resemble what is seen in the Milky Way, it can offer insight into the underlying processes that shaped those features. These simulations are not just visual tools, they are mathematical experiments testing how gravity, gas dynamics, star formation, and dark matter interact over billions of years. By adjusting the parameters of a model, such as the amount of dark matter or the rate of gas inflow, researchers can see how the galaxy's shape and behaviour change. This helps narrow down the range of possibilities for the Milky Way's true structure. One of the most significant challenges in all of this work is dealing with uncertainty. Every measurement has an error bar, a range of possible values within which the true answer likely lies. When you're measuring tiny shifts in star positions or faint signals from distant gas clouds, those uncertainties can be substantial. Building a coherent map from millions or billions of such measurements requires careful statistical analysis and a willingness to revise conclusions as new data become available. The Gaia mission is a good example of how this process unfolds. Its early data releases already transformed our understanding of the Milky Way, revealing streams of stars left behind by ancient mergers, ripples in the disk, and unexpected patterns in stellar motion. Later releases refined these results, corrected some earlier interpretations, and uncovered new details. The map of the galaxy is not a finished product. It is a living document, constantly being updated. There is also the challenge of scale. The Milky Way is so large that different parts of it are best studied with different techniques. The local neighbourhood can be mapped in exquisite detail using parallax and direct measurements. The inner regions require infrared and radio observations to penetrate dust. The outer halo is probed through faint stars and the motions of satellite galaxies. Each region has its own set of tools and its own sources of uncertainty. Despite these difficulties, a surprisingly coherent picture has emerged. The Milky Way is a barred spiral galaxy with a thin, warped disk, several major spiral arms, a dense central bulge and bar, and a vast extended halo dominated by dark matter. This picture is not drawn from a single image, but from the careful layering of many different kinds of data, each filling in a piece of the whole. There is something quietly remarkable about this. Humans, standing on a small planet in one corner of a galaxy, have found ways to measure the distances to stars thousands of light years away, to trace the motion of gas on the far side of the disk, and to infer the presence of invisible matter shaping the entire system. All of this is done by collecting tiny bits of information, a shift in colour here, a change in position there, and weaving them together into a map that spans 100,000 light years. At the same time, this process highlights how much remains beyond direct reach. Dark matter, which makes up a large fraction of the galaxy's mass, is still detected only through its gravitational effects. The farthest edges of the halo are poorly defined. The exact number and shape of the spiral arms are still debated. The strength and rotation rate of the bar are refined with each new study. This blend of knowledge and mystery is part of what gives the effort its character. Measuring the Milky Way is not about arriving at a final perfect answer. It is about continually improving a model, testing it against new observations and adjusting it when it falls short. The galaxy itself is not static, and neither is our understanding of it. From a more personal angle, there is something grounding about realizing that every clear number and neat diagram in a textbook is backed by this kind of careful, patient work. The map of the Milky Way is not a given. It is a human creation, built from generations of observation, invention and collaboration. It reflects not only the structure of the galaxy, but also the structure of human curiosity. As you think about this, the night sky can take on a slightly different quality. The stars are no longer just points of light. They are markers in a vast three-dimensional landscape that people are still learning how to navigate and describe. The dark lanes in the Milky Way are not just shadows. They are challenges, places where the map fades and the work continues. Looking ahead, new instruments and missions promise to push this effort even further. Larger radio arrays, more sensitive infrared telescopes, and future space observatories will probe deeper into the dust-shrouded centre and farther out into the faint halo. Each new data set will add detail and, inevitably, raise new questions. The act of tracing the galaxy's shape from within is, in a sense, a mirror of how we understand many things in life. We rarely get an outside view. We piece together our understanding from the inside, from limited perspectives and partial information, building models that help us make sense of a larger whole. The Milky Way, vast and complex, becomes both an object of study and a quiet metaphor for that process. Far outside the familiar glow of the Milky Way's bright disk, beyond the sweeping spiral arms and the crowded lanes of stars and dust, the galaxy does not simply stop. It fades. The light thins, the stars grow sparse, and the structure that once felt solid and defined becomes something more like a whisper. This is the realm known as the halo, a vast faint envelope that surrounds the visible galaxy and stretches far into space, shaping the Milky Way's true size in ways that are easy to overlook and difficult to fully imagine. The first thing to understand about the halo is that it does not look like much when you glance at the night sky. There is no obvious boundary where you can point and say, here is where the galaxy ends. Instead, the density of stars gradually decreases as you move away from the disk. The bright band of the Milky Way dissolves into isolated points of light, and then even those become few and far between. Yet, even in this apparent emptiness, the galaxy's influence continues. This outer region is populated by a different kind of stellar community. While the disk is rich in younger stars, glowing nebulae, and active star-forming regions, the halo is mostly home to ancient stars. Many of them formed early in the Milky Way's history, long before the spiral arms took on their present shape. These stars tend to be small, faint, and low in heavy elements, reflecting a time when the universe itself was younger and less enriched by generations of stellar birth and death. One of the most prominent features of the halo is the presence of globular clusters. These are dense, spherical groups of stars, often containing hundreds of thousands or even millions of members, all packed into a relatively small volume of space. Unlike the open clusters found in the disk, which are loosely bound and gradually disperse, globular clusters are tightly held together by gravity and can survive for billions of years. These clusters orbit the Milky Way far above and below the plane of the disk, tracing out wide, elongated paths through the halo. Their distribution was one of the key clues that helped astronomers realize the Sun was not at the center of the galaxy. By mapping where these clusters are located in the sky, researchers could infer the position of the galactic core, which lies in the direction where the clusters are most densely concentrated. Beyond the globular clusters and the scattered halo stars lies something even more elusive. the bulk of the halo's mass is not made of stars at all. It is dominated by dark matter, an invisible form of matter that does not emit, absorb, or reflect light. Its presence is revealed only through its gravitational effects on the visible parts of the galaxy. Without this dark matter halo, the Milky Way would not behave the way it does. The outer stars in the disk would not orbit as fast as they do. The spiral structure would be less stable. The galaxy itself might not even hold together over long periods of time. In this sense, the halo is not just a faint outer layer, it is the structural backbone of the entire system. The idea of dark matter emerged from attempts to understand how galaxies rotate. When astronomers measured the speeds of stars and gas at different distances from the centre of the Milky Way and other galaxies, they found something unexpected. Instead of slowing down as they moved farther out, as would be predicted by the gravity of the visible matter alone, the outer regions kept moving at high speeds. The only way to explain this was to assume there was a large amount of unseen mass extending well beyond the visible edge of the galaxy. This unseen mass forms a roughly spherical halo that envelops the disk and bulge. Estimates suggest that the dark matter halo of the Milky Way may extend several 100,000 light-years from the centre, far beyond the region where most of the stars reside. In terms of mass, it outweighs the visible components of the galaxy by a significant margin. Even though dark matter itself remains mysterious, its effects can be traced in subtle ways. The motions of satellite galaxies, small companions that orbit the Milky Way, provide one line of evidence. These galaxies move through the halo, their paths shaped by the gravitational pull of the Milky Way's mass. By studying their orbits, astronomers can infer the shape and extent of the dark matter distribution. Some of these satellite galaxies, like the Large and Small Magellanic Clouds, are visible to the naked eye from the southern hemisphere. Others are faint and difficult to detect, discovered only through careful surveys of the sky. Many of them appear to be in the process of being pulled apart by the Milky Way's gravity, their stars stretched into long, thin streams that wrap around the galaxy. These stellar streams are among the most revealing features of the halo. They are the remnants of smaller galaxies or star clusters that ventured too close to the Milky Way and were gradually torn apart. As their stars drift away, they trace out the gravitational field of the halo, like threads pulled through an invisible current. By mapping these streams, astronomers can learn about the shape of the dark matter halo itself. If the halo were perfectly spherical, the streams would follow relatively simple paths. If it is elongated or lopsided, the streams would be bent and twisted in characteristic ways. Current evidence suggests that the halo is not perfectly round but slightly stretched, though the exact details are still being refined. The halo also contains a faint diffuse glow from stars that are not bound to any cluster or stream. These stars move on wide, looping orbits that take them far from the disk and then back through it. Their motions are more random than those of disk stars, reflecting the turbulent history of the galaxy's growth. That history is written into the halo itself. The Milky Way did not form in isolation. Over billions of years, it has grown by absorbing smaller galaxies. Each merger leaves behind a signature, a population of stars with distinct motions and chemical compositions. By identifying these groups within the halo, astronomers can reconstruct a kind of family tree for the galaxy, tracing which parts came from where and when. Some of the stars in the halo are among the oldest known in the Milky Way, with ages approaching the age of the universe itself. Their chemical makeup shows that they formed at a time when heavy elements were rare, before many generations of stars had lived and died to enrich the interstellar medium. Studying these ancient stars provides a window into the early stages of galaxy formation, not just for the Milky Way, but for galaxies in general. Despite its importance, the halo is difficult to observe directly. Its stars are faint and spread out, making them hard to distinguish from the background. Many of the features within it, like stellar streams, are subtle, requiring precise measurements of star positions and motions to identify. This is where missions like Gaia have made a significant impact, revealing structures in the halo that were previously hidden in the noise. Even with these advances, much of the halo remains poorly defined. Its outer edge, in particular, is hard to pin down. The density of stars becomes so low that it is difficult to tell where the Milky Way ends and intergalactic space begins. In some directions, the halo may extend farther than in others, shaped by past interactions and the distribution of dark matter. This lack of a sharp boundary challenges the way we think about the galaxy's shape. The disk and spiral arms give the Milky Way a relatively clear outline in the plane of the galaxy. The halo, by contrast, is more like a gradient, a gradual transition from the structured, luminous core to the vast, dark spaces between galaxies. The true size of the Milky Way depends on how you define its edge, whether by the reach of its stars, the extent of its dark matter, or the limit of its gravitational influence. In a broader cosmic context, the halo is also where the Milky Way interacts most directly with its surroundings. Gas from intergalactic space can be pulled into the halo, cooling and eventually settling into the disk where it can fuel new rounds of star formation. At the same time, material can be pushed outward by supernova explosions and stellar winds, enriching the halo and the space beyond with heavy elements. This exchange of matter means that the halo is not just a passive outer shell. It is part of a continuous cycle, linking the galaxy to the larger environment of the universe. The Milky Way is embedded in a network of cosmic filaments and structures that extend across millions of light years. The halo is the interface between the galaxy and that larger web. There is something quietly striking about the idea that most of the Milky Way's mass is not in the stars you see, but in something you cannot. The bright band of the galaxy, so prominent in a dark sky, is just the visible surface of a much larger, mostly invisible structure. The halo, with its dark matter and faint stars, defines the galaxy's true reach and its long-term stability. From a human perspective, this can shift the way the night sky feels. The stars overhead are not the full story. They are the most obvious part of a much larger system that extends far beyond what the eye can detect. Even the emptiest-looking patches of sky may be filled with the gravitational presence of the galaxy, guiding the motion of distant stars and satellite galaxies. There is also a sense of time embedded in the halo. The ancient stars and long drifting streams are reminders of events that happened billions of years ago, when the Milky Way was still assembling itself from smaller pieces. The shape of the halo today is a record of those events, a kind of fossil imprint of the galaxy's formation and growth. As research continues, new questions keep emerging. How smooth is the dark matter distribution? Are there clumps and substructures within the halo? How much of the halo's mass is truly dark matter, and how much is in faint, undetected stars or gas? How does the halo interact with the disk over time, and how does it influence the formation and evolution of spiral arms and the central bar? Each of these questions points to the same underlying theme. The Milky Way's shape is not just defined by what shines, it is defined by what pulls. Gravity, acting through both visible and invisible matter, sculpts the galaxy on every scale, from the orbits of individual stars to the sweeping arcs of stellar streams in the halo. Letting this idea settle in can add another layer to the mental image of our galaxy. Instead of a flat, glowing pinwheel floating in empty space, the Milky Way becomes a luminous core wrapped in a vast, ghostly sphere, a structure that extends far beyond the reach of starlight. The halo is the reason the galaxy holds together, the reason its arms can persist, the reason its smaller companions remain bound. Invisible, yet quietly decisive, there is a presence in the Milky Way that never shows itself as a point of light or a glowing cloud, but without it the galaxy would not look or behave the way it does. This presence is dark matter, a form of matter that does not shine, does not cast shadows, and does not interact with light in any way we can directly detect. And still, it shapes the motion of stars, the sweep of spiral arms, the reach of the halo, and the long, slow dance of the entire galaxy through space. The idea of dark matter did not arise from a single dramatic discovery. It emerged gradually, as astronomers noticed small persistent mismatches between what they expected to see and what the universe actually did. The first clues came from studying how stars and gas move within galaxies. According to the laws of gravity as we understand them, the speed at which an object orbits should depend on how much mass lies inside its orbit. In a simple system, the farther out you go, the slower things should move, because there is less mass pulling inward. When astronomers applied this reasoning to the Milky Way and other spiral galaxies, they expected to see orbital speeds drop off in the outer regions of the disk. Instead, they found something surprising. Stars and gas far from the centre were moving just as fast as those much closer in. The rotation curve, a graph showing orbital speed versus distance from the centre, flattened out rather than declining. This flatness suggested that there was far more mass in the outer parts of the galaxy than could be accounted for by the visible stars and gas alone. At first, some scientists wondered whether their understanding of gravity might be incomplete on these large scales. Others considered whether there might be large amounts of faint, unseen matter, perhaps dim stars or cold gas clouds, lurking in the outskirts of galaxies. Over time, as observations improved and alternative explanations were tested, the idea of a new form of matter gained strength. This matter would have mass and exert gravity, but it would not interact with light. It would be, in every practical sense, dark. In the Milky Way, this dark component appears to form a vast halo that extends far beyond the visible disk and the faint halo of stars. While the luminous parts of the galaxy stretch out to perhaps 100,000 light-years, the dark matter halo may reach several times farther, creating a gravitational envelope that defines the galaxy's true size and influence. The shape of this halo is not something we can photograph or observe directly. Instead, it is inferred from the way it affects other things. The orbits of stars in the disk, the motion of globular clusters in the halo, and the paths of satellite galaxies all carry the imprint of the dark matter's distribution. By carefully measuring these motions, astronomers can begin to sketch an outline of something they cannot see. One of the most useful traces of the dark matter halo is the Milky Way's collection of small companion galaxies. These satellites, some of which are only faint smudges of stars, orbit the Milky Way under the influence of its gravity. Their speeds and trajectories depend on how mass is distributed in and around the galaxy. If the halo were small or sharply bounded, the satellite's orbits would look very different from what is observed. Instead, these companions move as if they are embedded in a much larger, more massive structure. Some follow elongated, looping paths that take them far from the disk before bringing them back in. Others appear to be slowly spiraling inward, gradually losing energy as they interact with the Milky Way's halo. By modelling these motions, astronomers can estimate the mass and shape of the dark matter distribution. Another line of evidence comes from stellar streams. These are long, thin trails of stars that have been pulled out of smaller galaxies or star clusters as they were torn apart by the Milky Way's gravity. Once freed, these stars continue to orbit the galaxy, forming arcs that can stretch across large portions of the sky. The exact shape of these arcs depends on the underlying gravitational field. If the dark matter halo were perfectly smooth and spherical, the streams would follow relatively simple, predictable paths. Deviations from this pattern can reveal lumps, elongations, or asymmetries in the halo. Studying these streams is a bit like watching leaves drift along an invisible current in a river. You cannot see the water itself, but the way the leaves move tells you about the flow beneath the surface. In the same way, the stars in a stream trace out the unseen structure of the dark matter halo. On even larger scales, the motion of gas in the outer disk provides additional clues. Hydrogen gas extends farther out than most of the stars, and its rotation can be measured using radio telescopes. The fact that this gas continues to move at high speeds far from the centre reinforces the picture of a massive extended halo. Without dark matter, the gas would not remain bound to the galaxy. It would drift away into intergalactic space. The presence of dark matter also helps explain why spiral galaxies like the Milky Way are so stable. The spiral pattern, with its sweeping arms and central bar, persists over billions of years. Simulations suggest that without the gravitational support of a massive halo, these structures would be more prone to disruption. The dark matter provides a kind of scaffolding, an underlying framework that helps hold the visible galaxy together. From a theoretical perspective, dark matter plays a role not just in shaping individual galaxies, but in the formation of the universe's large-scale structure. According to current models, tiny fluctuations in the density of dark matter in the early universe acted as seeds for the formation of galaxies and clusters. Ordinary matter, made of protons, neutrons and electrons, fell into these dark matter wells, cooling and condensing to form stars and galaxies. In this view, the Milky Way exists where it does because of a pattern laid down by dark matter billions of years ago. This connection between the smallest and largest scales adds another layer of significance to the halo. The dark matter surrounding the Milky Way is not just a local feature, it is part of a vast cosmic network, a web of invisible matter that stretches across the observable universe. Galaxies form at the intersections of this web, like knots in a vast three-dimensional net. Despite its central role in modern cosmology, the true nature of dark matter remains one of the biggest open questions in science. Many theories have been proposed about what it might be made of. Some suggest it consists of new, undiscovered particles that interact only weakly with ordinary matter. Others explore more exotic possibilities, including modifications to our understanding of gravity itself. Experiments on Earth and in space are searching for signs of dark matter particles. Sensitive detectors deep underground look for tiny flashes of light or heat that might be produced when a dark matter particle collides with an atom. Telescopes scan the sky for unusual patterns of radiation that could result from dark matter particles interacting with each other. So far, these efforts have not produced a definitive answer, but they continue to narrow down the range of possibilities. While the composition of dark matter is still unknown, its effects are unmistakable. In the Milky Way, its presence can be felt in the way stars move, in the shape of the halo, and in the behaviour of satellite galaxies. It defines the galaxy's gravitational footprint, extending far beyond the region of starlight and dust. There is also a more subtle influence. Dark matter affects how gas flows into the galaxy from intergalactic space. The halo's gravity can pull in streams of gas that eventually settle into the disk, providing fresh material for star formation. In this way, the invisible halo plays a role in the visible cycle of stellar birth and death. The relationship between dark matter and the central bar is another area of ongoing study. The distribution of dark matter in the inner regions of the galaxy can influence how the bar forms and evolves. A dense concentration of dark matter near the centre might slow the rotation of the bar over time, altering the pattern of resonances that shape the spiral arms. Understanding this interplay requires detailed models and precise observations of stellar motion in the inner Milky Way. From a practical standpoint, astronomers often build models of the galaxy that include both visible matter and dark matter. These models are tested against observations such as the rotation curve, the distribution of stars in the halo, and the motion of satellite galaxies. When the models match the data, confidence grows that the underlying assumptions are on the right track. When they do not, it signals that something important is missing or misunderstood. This iterative process of building, testing, and refining models is at the heart of how scientists approach something as elusive as dark matter. There is no single experiment or observation that can settle the question. Instead, progress comes from many small steps, each adding a piece to a larger picture. From a more human point of view, the idea of an invisible structure shaping everything around us can feel both unsettling and oddly comforting. It suggests that there are layers of reality beyond what our senses can detect, forces at work that are quiet but profound. The stars you see in the night sky are not just floating freely, they are embedded in a vast, unseen framework that guides their motion and holds them together. This perspective can also change how the Milky Way's shape is imagined. Instead of a simple, glowing spiral floating in empty space, the galaxy becomes a luminous core wrapped in a much larger invisible form. The visible arms and disk are like the surface of an iceberg, hinting at a much greater mass hidden below. The halo of dark matter blurs the boundary between the galaxy and the space around it. Where does the Milky Way truly end if its gravitational influence stretches far beyond its stars? Satellite galaxies can be found hundreds of thousands of light years away, still bound to the Milky Way's pull. Gas clouds drifting in the surrounding region can be drawn inward, becoming part of the galaxy over time. In this sense, the galaxy's shape is defined as much by reach as by appearance. There is also a temporal dimension to this invisible structure. The dark matter halo has likely been in place since the earlier stages of the Milky Way's formation. It has guided the assembly of the galaxy, influenced where stars formed, and shaped how the disk and spiral arms evolved. The present-day Milky Way is, in part, a visible expression of an ancient invisible pattern. As research continues, new techniques may reveal more about the fine structure of the halo. Future surveys of stellar streams, more precise measurements of star motions, and deeper observations of the galaxy's outskirts could uncover clumps and substructures in the dark matter distribution. These features would provide valuable clues about the nature of dark matter itself and the history of the Milky Way's growth. The effort to understand dark matter is, in many ways, an extension of the effort to understand the galaxy's shape. Both involve tracing the influence of something you cannot directly see. Both require a willingness to infer, to model, and to revise, and both remind us that the universe often reveals itself indirectly, through patterns and effects rather than through obvious displays. As this invisible framework comes into focus, the Milky Way's visible features take on new context. The spiral arms, the bar, the bulge, and the halo of stars are all nested within a much larger, darker structure that defines their motion and stability. The galaxy is not just a collection of luminous parts, it is a system held together by an unseen hand, a gentle but persistent grip that extends far beyond the glow of starlight. Following this thread naturally leads toward a broader comparison. If dark matter shapes the Milky Way in these ways, what about other galaxies? How similar or different are their invisible halos? Do they have the same kinds of structures, the same patterns of influence? Across the vast distances that separate the Milky Way from its nearest neighbours, there are countless other galaxies quietly turning in the dark, each one a variation on the same basic theme of stars, gas, gravity, and time. By looking outward at these distant systems, astronomers have found one of the most powerful ways to understand the structure of our own. When you cannot step outside your own galaxy to see its full shape, sometimes the best option is to study the reflections of it in others. The night sky, even to the naked eye, offers a hint of this broader perspective. Beyond the band of the Milky Way, there are a few faint cloudy patches that do not resolve into individual stars without a telescope. One of the most famous is the Andromeda Galaxy, a pale smudge visible from dark locations in the northern hemisphere. That faint glow is not a nebula or a cluster. It is another spiral galaxy, much like our own, seen from millions of light years away. Andromeda, also known as M31, is often the first point of comparison for the Milky Way. It is similar in size and mass, and it too is a barred spiral galaxy, with a central bulge, sweeping arms, and an extended halo. The key difference is that we can see Andromeda from the outside. Its full shape, including the curve of its arms and the structure of its disk, is laid out before us in a way that the Milky Way's never can be. By studying Andromeda, astronomers can test their ideas about how spiral galaxies are built and how they evolve. features that are difficult to trace in our own galaxy, such as the exact number and arrangement of spiral arms, or the shape of the central bar, can be examined more directly in Andromeda. When similar features appear in both systems, it adds confidence that the inferred structure of the Milky Way is on the right track. This process of comparison extends far beyond our nearest neighbour. Over the past century, astronomers have catalogued millions of galaxies, each with its own form and character. Some are grand, symmetrical spirals with clearly defined arms. Others are more patchy, with loosely organised structures. There are galaxies dominated by smooth, featureless disks, and others shaped by recent collisions or interactions. By placing the Milky Way within this broader family, scientists can begin to see which of its features are typical and which might be unusual. One of the first insights gained from this wider view is that spiral galaxies are not all built the same way. The classic image of a perfect pinwheel-like structure, with 2 or 3 elegant arms winding outward from a bright core, represents only one end of a spectrum. Many spirals have bars at their centres, like the Milky Way. Others do not. Some have tightly wound arms, while others have arms that are open and loosely defined. The Milky Way appears to fall somewhere in the middle. Its bar is prominent but not as dominant as in some galaxies. Its spiral arms are present, but they are not as sharply defined as in the most symmetrical Gaza grand design spirals. This places our galaxy in a category known as a barred spiral with moderate arm structure, a common type in the nearby universe. Looking at other barred spirals provides clues about how the bar in the Milky Way might influence its overall shape. In many external galaxies, the spiral arms can be seen to emerge from the ends of the bar rather than directly from the central bulge. This pattern supports the idea that the bar plays a key role in organising the flow of gas and stars in the inner regions of the disk, guiding material into the arms and helping maintain their structure over time. Another useful point of comparison comes from galaxies that are seen edge-on. These systems present their disks as thin lines across the sky, with a bright bulge in the middle and a faint halo extending above and below. From these views, astronomers can study the vertical structure of galaxies, measuring how thick the disk is and how the halo of stars and dust is distributed. The Milky Way, when inferred from data, appears to have a thin disk embedded within a thicker, more diffuse component. This two-layer structure is seen in many other spiral galaxies as well. The thin disk is rich in young stars and gas, where star formation is active. The thick disk contains older stars that move in more tilted orbits, suggesting a more turbulent past, possibly shaped by mergers and interactions. By comparing these features across many galaxies, scientists can piece together a general story of how spiral galaxies grow and change. The presence of a thick disk in both the Milky Way and other systems hints that early in their histories, these galaxies experienced periods of disturbance, such as collisions with smaller galaxies, or large-scale instabilities that stirred up their stellar populations. The halos of other galaxies also provide valuable context. In deep images, faint streams of stars can be seen arcing around nearby spirals, the remnants of smaller galaxies being pulled apart by gravity. These features mirror the stellar streams found in the Milky Way's own halo. The similarity suggests that galaxy growth through mergers is not unique to our home. It is a common process in the universe. By measuring the motions of stars and gas in other galaxies, astronomers can study the distribution of dark matter in those systems as well. Rotation curves of distant spirals show the same flat behaviour seen in the Milky Way, indicating that extended dark matter halos are a general feature of spiral galaxies. This reinforces the idea that the invisible framework shaping our galaxy is part of a universal pattern. There is also something to be learned from galaxies that look very different from the Milky Way. Elliptical galaxies, for example, lack the disk and spiral structure entirely. They are more like three-dimensional swarms of stars with little gas and very little ongoing star formation. Studying these systems helps clarify what conditions are necessary for spiral arms and disks to form and persist. Irregular galaxies, which have no clear organised shape, often show signs of recent interactions or low mass. Comparing these with the Milky Way highlights the role of mass and environment in shaping galactic form. A large, massive galaxy like ours has enough gravity to maintain a stable disk and to draw in smaller companions, shaping itself over time through a series of mergers and accretions. The environment in which a galaxy lives also matters. The Milky Way is part of a small group of galaxies known as the Local Group, which includes Andromeda, the Triangulum Galaxy, and dozens of smaller companions. These galaxies are gravitationally bound to each other and will, over very long timescales, interact more closely. Andromeda and the Milky Way in particular are on a slow collision course. In about 4 billion years they are expected to begin merging, eventually forming a single, larger galaxy. Observing other galaxy mergers at different stages of this process gives astronomers a preview of what might happen to our own. These observations show how disks can be disrupted, how star formation can be triggered, and how the final shape of a merged galaxy can differ dramatically from its original components. By studying galaxies in clusters, where hundreds or thousands of galaxies are packed into a relatively small region of space, scientists can see how extreme environments affect galactic shape. In these crowded settings, interactions are frequent. Gas can be stripped away, star formation can be shut down, and spiral structures can be transformed into smoother, more featureless forms. The fact that the Milky Way retains its spiral shape suggests that its environment has been relatively calm, with fewer disruptive encounters compared to galaxies in dense clusters. The role of gas is another area where comparisons are revealing. Some spiral galaxies are rich in cold gas, fueling active star formation and bright, well-defined arms. Others have used up or lost much of their gas and appear more subdued, with fainter arms and older stellar populations. The Milky Way sits somewhere in between, still forming stars at a steady pace, but not at the intense rates seen in some more gas-rich systems. This balance influences the appearance of the galaxy. The presence of young, hot stars in the spiral arms makes them stand out in blue and ultraviolet light, while older stars contribute more to the overall smoother glow of the disk. Observing these patterns in other galaxies helps astronomers interpret what they see in the Milky Way's own star fields and dust lanes. One of the more subtle lessons from looking outward is that no two galaxies are exactly alike. Even among systems that share the same basic classification, there are differences in the number of arms, the strength of the bar, the size of the bulge, and the shape of the halo. This diversity reflects the unique history of each galaxy, shaped by its initial conditions and its interactions over billions of years. In this context, the Milky Way becomes one example in a much larger set, rather than a singular, isolated object. Its shape, with its moderate bar, multiple spiral arms, and extended halo, fits comfortably within the range of forms seen in the nearby universe. This suggests that while our galaxy has its own story, it is following a path that many others have taken as well. Looking at other galaxies also helps refine the models used to understand our own. Computer simulations of galaxy formation and evolution are tested against the wide variety of observed shapes and behaviours. If a model can produce galaxies that resemble both the Milky Way and its neighbours, it is more likely to capture the essential physics at work. When a model fails to reproduce certain features, it points to gaps in our understanding. These simulations often reveal that small changes in initial conditions can lead to noticeable differences in galactic form. The timing and size of mergers, the amount of gas available for star formation, and the distribution of dark matter all play roles in shaping the final outcome. This sensitivity helps explain why galaxies that look broadly similar can still have distinct personalities. There is also a cultural and historical dimension to this broader view. For much of human history, the Milky Way was thought to be the entire universe. the discovery that the faint, spiral-shaped nebulae in the sky were actually separate galaxies expanded our sense of scale in a dramatic way. Suddenly, our home galaxy became one among billions, each with its own stars, planets, and perhaps its own forms of life. This shift in perspective continues to influence how astronomers think about the Milky Way's shape. Instead of asking only, "What does our galaxy look like?" they also ask, "How does our galaxy compare?" The answers to that second question often feed back into the first, refining the mental image of our own home. There is something quietly grounding about realizing that the Milky Way's form is not unique or isolated. The spiral pattern, the central bar, the extended halo, and the influence of dark matter are all features shared with many other galaxies. The night sky, in this sense, becomes a local expression of a much larger, repeating pattern in the universe. At the same time, the differences matter too. The exact arrangement of arms, the size of the bulge, the current rate of star formation, and the specific history of mergers and interactions give the Milky Way its own character. These details shape the environment in which our solar system exists and influence the broader conditions of our corner of the cosmos. As more powerful telescopes come online, such as those capable of observing in new wavelengths or capturing extremely deep images of distant galaxies, the catalogue of known galactic forms continues to grow. Each new system adds another data point, another comparison that can be used to test and refine ideas about how galaxies like the Milky Way are structured. This outward-looking approach naturally circles back to our starting point. The Milky Way's shape, inferred from within, gains clarity when placed alongside the shapes of other galaxies seen from the outside. The curved arms traced in radio maps, the bar revealed in infrared surveys, and the halo inferred from stellar streams all find echoes in the forms of neighbouring systems. In this way, the universe itself becomes a kind of mirror. By studying distant galaxies, we catch glimpses of our own, reflected back at us across millions of light years. The patterns of light and shadow, the balance between visible matter and dark matter, and the long, slow evolution of structure are shared themes, written on a grand scale across the cosmos. Over the span of billions of years, the Milky Way has never truly held still. What looks, from a human lifetime, like a stable and unchanging band of light, is actually part of a system in constant motion, stretching, folding, and reshaping itself under the quiet guidance of gravity and time. The spiral form we recognize today is not a finished product. It is a moment in a long unfolding process, one that began not long after the universe itself and continues even now as you listen. In its earliest days, the Milky Way did not resemble a spiral at all. The young universe was a much simpler place, filled with clouds of hydrogen and helium drifting through space, guided by the uneven distribution of dark matter. Where these clouds gathered into dense regions, gravity took over, pulling matter inward and forming the first small collections of stars. These early structures were more like loose, irregular clumps than the organized galaxy we inhabit today. Over time, these clumps merged, collided, and combined, growing into a larger, more coherent system. Each merger added mass, stirred up motion, and left behind streams of stars that carried the memory of their former homes. The halo of the Milky Way, with its ancient stars and faint stellar streams, is a record of this early chaotic period, when the galaxy was assembling itself from many smaller pieces. As the mass of the forming galaxy increased, so did its ability to draw in gas from its surroundings. This gas, cooling and settling into a rotating disk, laid the foundation for the spiral structure that would later emerge. Rotation played a crucial role here. As the disk spun, it flattened, spreading out into a broad, thin plane. Within this plane, small variations in density grew over time, eventually giving rise to the sweeping arms that define the Milky Way's shape today. Star formation has been one of the main drivers of change throughout this process. In the dense regions of the disk, clouds of gas collapse under their own gravity, forming new stars. These stars do not simply light up and fade away quietly. The most massive among them live fast and die young, releasing enormous amounts of energy through intense radiation, powerful stellar winds, and, ultimately, supernova explosions. These events push surrounding gas outward, compress nearby clouds, and enrich the interstellar medium with heavy elements. This cycle of birth and death creates a kind of feedback loop. Star formation shapes the environment, and the environment in turn shapes where and how new stars can form. Over millions of years, this feedback influences the structure of the spiral arms, the thickness of the disk, and the overall appearance of the galaxy. The arms themselves are not permanent features carved into the galaxy's fabric. They are patterns that move through the disk, regions where gas and stars tend to gather as they orbit the centre. A star born in one arm will, over time, drift away from it, crossing into interarm space, and perhaps entering another arm later in its journey around the galaxy. The arms persist as a pattern, even though the material within them is constantly changing. This constant flow gives the Milky Way a living quality. It is not a static pinwheel frozen in space, but a dynamic system, with matter circulating, stars migrating, and structures evolving. The Sun's own path reflects this. Over the course of its long orbit around the galactic centre, it has likely passed through spiral arms, emerging from denser, brighter regions into quieter stretches of the disk. Each passage would have brought subtle changes to the surrounding environment, from variations in nearby star density to shifts in the intensity of cosmic radiation. The disk itself is not perfectly flat. Observations have revealed that it is warped, bending upward in some directions and downward in others. This warp is most noticeable in the outer regions, where the gravitational influence of the central mass is weaker, and the pull of nearby galaxies or the uneven distribution of dark matter can have a greater effect. The causes of this warp are still being studied, but interactions with the Milky Way's satellite galaxies are a leading possibility. The Large and Small Magellanic Clouds, two relatively large companions, orbit the Milky Way and exert gravitational forces that can tug on the outer disk. Over long periods, this tugging can create ripples and bends, much like a gentle but persistent breeze shaping the surface of a lake. In addition to this large-scale warp, the disk shows smaller waves and ripples, patterns of stars moving up and down relative to the galactic plane. These vertical motions may be the result of past encounters with smaller galaxies, or massive clouds of gas that pass through the disk, sending disturbances that are still propagating through the stellar population. The central bar also evolves over time. Simulations suggest that bars can grow stronger or weaker, depending on how mass is distributed within the galaxy. The flow of gas into the central regions can feed star formation, and build up the central bulge, altering the balance of forces that maintain the bar's shape. Interactions with the dark matter halo can slow the bar's rotation, changing the locations of resonances that influence the spiral arms. These internal processes are only part of the story. The Milky Way does not exist in isolation. It is part of a small group of galaxies bound together by gravity, and over billions of years, this group has been a source of both growth and disturbance. Smaller galaxies have been drawn in and absorbed, adding stars, gas, and dark matter to the Milky Way's mass. Each merger leaves its mark. The stars from an incoming galaxy are stretched into long streams, wrapping around the Milky Way in graceful arcs. Over time, these streams disperse, blending into the halo, but their presence can still be detected through careful measurements of stellar motion and composition. These features are like faint scars, reminders of past encounters that helped shape the galaxy's present form. Some of these mergers may have played a role in thickening the Milky Way's disk. The thin disk, where most of the younger stars and gas reside, is embedded within a thicker disk of older stars. This thicker component may have formed during a period of more frequent interactions, when the disk was stirred and heated by incoming material. Gas accretion is another important source of change. The Milky Way continues to draw in gas from its surroundings, both from the remnants of small galaxies and from the diffuse intergalactic medium. This gas can settle into the disk, replenishing the supply needed for star formation. Without this ongoing inflow, the galaxy would eventually exhaust its gas, and star formation would slow to a crawl. The halo plays a role in this process as well. Gas passing through the halo can cool and condense, forming clouds that fall toward the disk. At the same time, energetic events in the disk, such as supernovae, can push gas outward into the halo, where it may later rain back down. This exchange creates a slow, circulating flow of matter between the disk and the halo, linking the bright active regions of the galaxy to its faint extended outskirts. The future of the Milky Way is shaped by these same forces, but one event stands out as particularly significant. The slow approach of the Andromeda galaxy is setting the stage for a major transformation. Observations show that Andromeda is moving toward us, and in a few billion years, the two galaxies will begin a long, complex merger. This will not be a single dramatic collision, but a series of close passes where the two systems pull on each other, distort each other's shapes, and fling out long tidal tails of stars and gas. Over time, their disks will be disrupted, their spiral structures blurred, and their stars mixed into a new, larger galaxy. From the perspective of any future observers on Earth, if Earth still exists, the night sky would change dramatically. Andromeda would grow larger and brighter over millions of years, eventually filling a large portion of the sky as the two galaxies interact. The familiar band of the Milky Way would be joined by streams of stars pulled from both systems, creating a complex, evolving pattern of light and shadow. In the end, the merged galaxy is expected to settle into a more rounded, elliptical shape, lacking the clear spiral arms that define the Milky Way today. The central black holes of the two galaxies will likely merge as well, forming an even more massive object at the core of the new system. The galaxy that emerges will be very different from the one we know now, a reminder that even structures on this vast scale are temporary. On smaller timescales, changes continue in quieter ways. Individual star clusters drift apart as their members move under the influence of the galaxy's gravitational field. New clusters form in the spiral arms. Supernova explosions send shockwaves through the interstellar medium, carving out bubbles of hot gas that expand and fade. The chemical composition of the galaxy slowly evolves as heavy elements produced in stars are mixed into new generations of gas and dust. The Milky Way's shape at any given moment is a snapshot of all these processes combined. The spiral arms reflect the current pattern of density waves and star formation. The bar reflects the distribution of mass and the dynamics of the inner disk. The halo reflects the long history of mergers and accretion. Each component tells a different part of the story. There is also a connection between the galaxy's evolution and the broader universe. The Milky Way is embedded in a cosmic web of dark matter and gas that stretches across millions of light years. Its motion through this web influences how it accretes material and how it interacts with neighbouring galaxies. Changes in this larger environment can ripple down to affect the galaxy's own structure. From a scientific perspective, studying how the Milky Way changes over time helps test theories of galaxy formation and evolution. By comparing the Milky Way to galaxies at different stages of development, astronomers can piece together a timeline of how spirals form, how bars emerge, and how disks grow and warp. Observations of distant galaxies, whose light has taken billions of years to reach us, provide glimpses of earlier stages in this process, offering a kind of time machine for understanding our own galaxy's past. At a more reflective level, there is something quietly profound about realizing that the Milky Way is not a permanent backdrop, but a living system. The stars you see tonight are part of a flow that began long before Earth existed and will continue long after. The shape of the galaxy is not a fixed outline, but a pattern that shifts and adapts, shaped by both internal rhythms and external encounters. This sense of motion can bring a different quality to the night sky. The band of light overhead becomes not just a beautiful feature, but a sign of ongoing change, a reminder that everything, even something as vast as a galaxy, is part of a larger, evolving story. As the view extends forward in time, it also invites a return to the present. The Milky Way you see now is the product of billions of years of growth, bending, merging, and reshaping. It is a temporary form, one that exists for a brief window in the long life of the universe. Long before any dramatic moment arrives, the future of the Milky Way begins with something almost unnoticeable. It starts with a slow, steady motion across the vastness of space, a gentle closing of distance between our galaxy and its largest neighbour. This neighbour, the Andromeda Galaxy, has been drifting toward us for billions of years, guided by the quiet pull of gravity. The space between the two is immense, measured in millions of light years, yet even that span is not enough to keep them forever apart. Astronomers know about this motion because of the light Andromeda sends our way. When that light is examined closely, its wavelengths are slightly shifted toward the blue end of the spectrum. This shift indicates that Andromeda is moving toward us rather than away. In a universe where most galaxies are receding as space itself expands, this inward motion stands out. It signals that the gravitational bond between the Milky Way and Andromeda is strong enough to overcome the general expansion of the cosmos, at least on this local scale. The current distance between the two galaxies is about 2.5 million light-years. That number is difficult to picture in any ordinary sense. If you could travel at the speed of light, which nothing with mass can do, it would still take 2.5 million years to make the journey. And yet, over cosmic timescales, this distance is relatively small. The local group, the small collection of galaxies that includes the Milky Way, Andromeda, and dozens of smaller companions, is a tightly knit neighbourhood in the vast cosmic web. The approach of Andromeda is not fast. It is measured in a few hundred kilometres per second, a speed that seems large by human standards, but is modest on a galactic scale. At this pace, it will take roughly 4 billion years before the two galaxies begin their first close encounter. By that time, Earth itself will be a very different place, if it still exists at all. The Sun will be older, brighter, and nearing the later stages of its life. The continents will have shifted. The night sky, however, will hold a new and growing presence. As Andromeda draws closer, it will gradually become more prominent in the sky. What is now a faint smudge visible only from dark locations will expand into a clearly defined spiral, its arms and core standing out against the stars. Over millions of years, it will grow larger and brighter, eventually becoming one of the most striking features of the night. The first close pass between the Milky Way and Andromeda will not be a direct head-on collision. Space is vast, and even when two galaxies overlap, the chances of individual stars colliding are extremely small. The real interaction happens through gravity. As the two systems approach, their gravitational fields will begin to pull on each other, stretching and distorting their shapes. Long streams of stars and gas, known as tidal tails, will be drawn out from both galaxies. These tails can extend for hundreds of thousands of light-years, forming sweeping arcs that curve through space. Within these streams, stars will follow new paths, some bound to the merged system that is forming, others flung outward into intergalactic space. The spiral structure of both galaxies will be disrupted. The elegant arms that define their current shapes will be twisted and blurred, losing their clear outlines. The central bars and bulges will feel the pull as well, their orbits shifting as the mass distribution changes. Over time, the two galaxies will pass through each other, then swing apart, only to be drawn back together again. This process will repeat over several billion years. Each pass will further mix the stars and gas, redistributing angular momentum and energy. Gradually, the two systems will lose their distinct identities, settling into a single, larger galaxy. This final product is often referred to as Milkdromeda or Milkdromeda, a name that reflects its dual origins. The shape of this merged galaxy is expected to be very different from the spiral form the Milky Way has today. Simulations suggest that the end result will likely be an elliptical galaxy, or something close to it. Instead of a flat disk with spiral arms, the stars will be arranged in a more rounded three-dimensional swarm. Their orbits will be more random, less confined to a single plane. The gas content of the system will play an important role in this transformation. As the two galaxies interact, their gas clouds will collide and compress, triggering bursts of star formation. These starbursts can be intense, lighting up the merging system with the glow of countless young massive stars. Over time, however, much of the gas will be used up or heated and dispersed, reducing the ability of the merged galaxy to form new stars. At the very centres of both the Milky Way and Andromeda lie supermassive black holes. As the galaxies merge, these black holes will eventually find each other and begin a slow, spiralling dance of their own. They will orbit around a common centre, gradually losing energy through interactions with surrounding stars and, in the final stages, through the emission of gravitational waves. When they finally merge, the event will release an enormous amount of energy in the form of ripples in space-time, though this will occur long after the galaxies themselves have combined into a single structure. The merged black hole will sit at the heart of the new galaxy, more massive than either of its predecessors, a silent anchor at the core of the system. From the perspective of any planets or civilizations that might exist in the distant future, the sky during this period would be unlike anything we can see today. The familiar band of the Milky Way would be joined by streams of stars pulled from Andromeda, creating a complex, shifting pattern of light. Over time, as the merger progresses, the sky might become filled with a diffuse glow as the combined galaxy stars spread out into a broader, more rounded distribution. While this future might sound dramatic, it is also a natural part of how galaxies grow and change. The Milky Way has experienced mergers before. The halo is filled with the remnants of smaller galaxies that were absorbed over billions of years. The difference with Andromeda is simply one of scale. This will be a major event, reshaping the galaxy on a grand level. Beyond Andromeda, there are other members of the local group that will be drawn into this evolving system. The Triangulum galaxy, another spiral, is also bound by gravity to the Milky Way and Andromeda. Its future is less certain. It may merge with one of the larger galaxies before they combine with each other, or it may become part of the final merged system later on. Smaller satellite galaxies will continue to orbit and in many cases be absorbed as well. Over time, the local group will likely consolidate into a single large galaxy, surrounded by a sparse halo of remaining companions. This process reflects a broader trend in the universe, where small structures merge to form larger ones, guided by the underlying distribution of dark matter. The dark matter halos of the Milky Way and Andromeda will also merge, creating an even more massive extended halo around the new galaxy. This combined halo will define the gravitational reach of the system, influencing the motion of stars and any remaining satellites over hundreds of thousands of light years. Even as this local drama unfolds, the universe on larger scales will continue to expand. Galaxies beyond the local group will gradually recede from view, their light stretched and dimmed by the expansion of space. Over extremely long timescales, the merged Milky Way and Andromeda system may become increasingly isolated, surrounded by a growing emptiness as distant galaxies slip beyond the cosmic horizon. This future isolation adds a different perspective to the idea of the galaxy's shape. Today the Milky Way is one among billions, part of a richly populated universe. In the far future it may become the dominant, perhaps the only visible galaxy in its region of space. Its shape will then be the primary structure in the night sky, defining the cosmic environment for any observers that remain. The long-term fate of stars within this future galaxy will also follow a gradual path. Star formation will likely slow as gas supplies diminish. The galaxy will become populated mostly by older, redder stars. The bright blue regions of active starbirth that mark the spiral arms today will fade into memory, replaced by a smoother, more uniform glow. On even longer timescales, individual stars will exhaust their fuel and evolve into white dwarfs, neutron stars, or black holes. The galaxy will become a quieter place, its light slowly dimming as the population of shining stars declines. The shape of the galaxy will still exist, defined by the distribution of these stellar remnants and the dark matter halo, but its luminous presence will be more subdued. Thinking about this distant future can give the present a different feel. The Milky Way's current spiral form, with its arms, bar and active star-forming regions, is a temporary phase in a much longer story. It is a shape that exists for a window of time, shaped by past events and moving toward future ones. The idea of a slow, inevitable merger with Andromeda also highlights the scale at which cosmic change operates. What seems permanent on human timescales is fluid and dynamic over billions of years. The sky above is not a fixed ceiling, but a shifting landscape, one that will look very different to observers in the far future. At the same time, there is a sense of continuity in this process. The stars that make up the Milky Way will not vanish in the merger. They will continue to exist, following new orbits in a new structure. The atoms that form those stars and any planets or life around them will still be part of the same cosmic material, simply rearranged on a larger scale. This perspective can make the galaxy's shape feel less like a rigid form and more like a phase in an ongoing transformation. The spiral we see today is one expression of a system that has been changing since the early universe and will continue to change long into the future. The future collision is distant, measured in billions of years, yet its seeds are already in motion. The Milky Way and Andromeda are already bound, already moving toward each other, already part of a shared gravitational story. The shape of our galaxy, then, is not just defined by what it is, but by what it is becoming. The arms, the bar, the halo, and the invisible framework of dark matter are all parts of a system in motion, guided by forces that operate on timescales far beyond everyday experience. Here, beneath the quiet sweep of the night sky, the immense structure you've been tracing through thought and imagination settles back into something simple and close. The Milky Way is no longer a diagram of arms and halos, no longer a distant system of dark matter and drifting galaxies. It becomes a soft band of light stretching from one horizon to the other, a familiar presence above rooftops, trees, open fields, or quiet streets. After travelling outward to the edge of the halo and forward to a future shaped by slow, inevitable motion, the journey returns to this moment, to the place where the galaxy meets the ground beneath your feet. When you look up from Earth, the shape of the Milky Way does not announce itself as a spiral or a barred system or a luminous disk wrapped in an invisible halo. It appears instead as a gentle glow, sometimes bright and crowded with stars, sometimes thin and faint, depending on where you are and which direction you face. The grand structure you have been considering exists all at once above you, yet only a small part of it is ever visible at any given time. What you see is a surface impression, a cross-section of a much larger form, filtered through atmosphere, distance, and the limits of human vision. The ground you stand on is moving, though it does not feel like it. Earth is turning on its axis, carrying you through day and night. At the same time, it is orbiting the Sun, tracing a wide path through space. The Sun, in turn, is orbiting the centre of the Milky Way, completing one full journey roughly every 200 million years. All of this motion is layered, one cycle nested inside another, like slow, overlapping rhythms. The galaxy overhead is not a static ceiling. It is a moving environment, and you are part of that motion. This sense of being carried can change how the night sky feels. The Milky Way is not just something you observe, it is something you are inside of. The stars that form its glowing band are not distant decorations placed against a black background. They are neighbours in a vast shared system, separated by great distances, but bound together by gravity and time. The shape of the galaxy, so complex when described in maps and models, becomes something softer in this context. The spiral arms are not visible as sweeping curves, but their presence is hinted at in the brighter regions of the Milky Way's band. The central bar does not appear as a straight line of stars, but the direction toward the crowded, luminous core marks where that structure lies. The halo does not reveal itself as a faint sphere, but its influence is there in the motion of the stars you see, in the stability of the pattern overhead. Even the invisible parts of the galaxy, the dark matter that shapes everything without showing itself, have a quiet connection to this moment. The reason the Milky Way holds together, the reason the stars continue their long orbits instead of drifting away, is tied to that unseen framework. The ground beneath you, the planet beneath that ground, and the star beneath that planet are all moving within a gravitational structure far larger than anything that I can trace. There is something steadying about that idea. The galaxy's shape is vast and complex, but it is also reliable. The stars rise and set in familiar patterns. The Milky Way arcs across the sky in predictable ways, changing with the seasons and the time of night. The structure overhead becomes a kind of clock, marking the slow passage of time on scales far beyond days or years. In different parts of the world, the view of the Milky Way changes. From the northern hemisphere, the bright core rises in the summer months, filling the sky with dense star fields and dark lanes of dust. In the winter, the band grows fainter and thinner, stretching across the sky in a more subtle line. From the southern hemisphere, the centre of the galaxy passes almost overhead, offering a view of some of the richest and most detailed regions of the Milky Way. These differences in perspective are small echoes of the larger truth about the galaxy's shape. Where you stand matters. The same structure can look very different depending on where you are inside it. This is true on the scale of the Earth, and it is true on the scale of the galaxy itself. Our position in the Orion spur between two major spiral arms shapes what we see and what we have to infer. The night sky can become a kind of quiet interface between the personal and the cosmic. The Milky Way overhead is part of a system that stretches for hundreds of thousands of light years, yet the experience of looking at it happens in a single moment, in a single place. The vast and the immediate meet in that simple act of turning your gaze upward. There is also a sense of continuity that runs through this view. The light from many of the stars in the Milky Way has been travelling for thousands, sometimes tens of thousands of years before reaching your eyes. That means the glow you see is a record of the past, a collection of moments from different times woven together into a single image. The galaxy's shape, as you perceive it, is a blend of history and present, layered into a single, soft band of light. The dust lanes that cut through the Milky Way add another layer to this experience. They appear as dark, winding shapes against the brighter background, giving the band texture and depth. These lanes are not empty spaces. They are dense clouds of material, the raw ingredients for future stars and planets. The shadows you see are places where light is being blocked, but they are also places where new light will one day be born. This cycle of light and shadow, of visibility and invisibility, reflects the larger story of the galaxy's shape. The Milky Way is defined as much by what you cannot see as by what you can. The halo of dark matter, the faint outer stars, the cold gas drifting far from the disk, all contribute to the galaxy's form, even though they do not announce themselves in the night sky. Letting this idea rest can make the view overhead feel deeper, layered with meanings and connections. The band of light becomes more than a pattern. It becomes a sign of a system in motion, a structure built over billions of years, shaped by mergers, star formation, gravity, and the quiet influence of invisible matter. There is also a human story woven into this view. For most of human history, the Milky Way was a mystery, a luminous river or path across the sky, interpreted through myth and imagination. Only in the last few centuries did it become clear that this glow is made of countless distant stars, and only in the last few decades have we begun to map its full shape with any real detail. The fact that people, standing on a small planet in one arm of a vast galaxy, have been able to piece together the structure of the system they live in is itself a remarkable part of the story. It reflects a long tradition of curiosity, observation, and careful reasoning, stretching from early sky watchers to modern astronomers using space-based telescopes and supercomputers. Yet even with all this knowledge, the experience of the night sky remains simple. You do not need to know about density waves, dark matter halos, or galactic bars to feel the presence of the Milky Way overhead. The soft glow, the scattered stars, and the dark lanes speak on their own, in a language that does not require equations or models. This simplicity can be comforting. The galaxy's true shape is vast and complex, but your connection to it does not have to be. It can be as straightforward as noticing a bright patch of sky, tracing a line of stars with your eyes, or recognizing the familiar curve of the Milky Way as it rises or sets. There is also a sense of belonging that can come from this view. The atoms that make up your body were formed in stars long before the sun existed. They are part of the same cycle of matter that shapes the galaxy. In a very literal sense, you're made of the same material that glows in the Milky Way's band. The shape of the galaxy is not just something you observe, it is part of what you are. This connection does not require any grand conclusion. It does not need to be framed as a final insight or a closing thought. It can simply be allowed to exist, like the quiet presence of the night sky itself. The Milky Way does not rush. It moves on timescales that stretch far beyond human lives, and there is no need to hurry to the end of its story. As you let your attention rest here, on this quiet meeting point between Earth and the galaxy, the larger journey does not truly stop. The stars continue their orbits. The spiral pattern continues to shift and evolve. The halo continues to guide the motion of everything within it. The distant future, with its slow approach of Andromeda and its eventual merging of systems, remains far ahead, unfolding at its own pace. What remains in the present is this simple view, this moment beneath a structure that is both familiar and vast. The shape you have been exploring through thought and description is also a shape you can feel, in the sense of being carried within it, moving along with the planet, the star, and the galaxy as part of a larger flow. From here, the path does not need to lead anywhere in particular. The Milky Way overhead can remain what it has always been, a quiet, steady presence, a reminder of a larger system in motion, and a gentle backdrop to a single, grounded moment on Earth. The glow across the sky continues its slow arc. The stars hold their positions for now, and the structure that spans hundreds of thousands of light years settles back into the simple experience of being seen from right where you are.